Some nights the world feels wider than it should. Light moves through your window without sound. It crossed 93 million miles of empty space just to land on your skin. 8 minutes ago, it left the surface of the sun. You blink and photons flood your retina. Tiny particles that behave like waves. Waves that collapse into particles when you try to measure them. Scientists call this wave-particle duality, and even they admit it makes no sense. Richard Feynman once said, "Nobody truly understands quantum mechanics." He won a Nobel Prize for studying it. Maybe that's the beauty. Not everything needs to be understood. Some things just are. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you. Now, let's drift. Tonight, we're tracing light. Not the light you think you know, but the light that remembers the light that bends time, the light that built everything you've ever touched. You exist because of light. Every atom in your body was forged inside a star, and light carried that story across billions of years. Carbon in your bones, iron in your blood, oxygen in your breath. All of it came from fusion reactions deep inside dying stars. And when those stars exploded, light scattered their elements across the cosmos. Eventually, those particles gathered into planets, into oceans, into you. Light doesn't just illuminate, it creates. Right now, your eyes are catching photons that left distant galaxies before humans existed. Some of that starlight has been traveling for millions of years. When you look up at the night sky, you're seeing the past. You're looking at ancient light that outlived entire civilizations. Light moves at 299,792,458 meters per second. Not approximately, exactly. Scientists define the meter based on how far light travels in a fraction of a second. Time and distance aren't separate anymore. They're woven together by light's constant speed. Einstein realized this in 1905. He imagined what would happen if you could ride a beam of light. Would time stop? Would space collapse? His thought experiments led to special relativity, and suddenly the universe got stranger. Nothing can move faster than light. Not because we lack the technology, but because the universe won't allow it. As objects approach light speed, time slows down for them. Their mass increases. Space contracts in the direction of motion. These aren't theories anymore. Scientists measure this effect in particle accelerators every day. Muons created in Earth's upper atmosphere shouldn't reach the ground before decaying, but they do. Time dilation keeps them alive long enough. Light built the rules, and everything else obeys. You see color because light knows how to dance with electrons. When photons hit an object, some wavelengths get absorbed and others bounce back. A red apple absorbs every color except red. Red light reflects into your eyes, and your brain interprets it. But here's the strange part. Color doesn't exist outside your mind. There's no redness in the photon, just a wavelength around 700 nanometers. Your brain invented the experience of red. Every color you've ever seen is a story your neurons tell themselves. Light bends. Newton thought light traveled in the straight lines, but Einstein proved gravity curves space itself, and light follows those curves. During a solar eclipse in 1919, astronomers measured starlight bending around the sun. The angle matched Einstein's predictions perfectly. Suddenly, light wasn't just fast, it was honest. It showed us the shape of space-time. Gravitational lensing happens when massive objects warp space so severely that light from distant galaxies curves around them. We can see galaxies that would otherwise be hidden behind other galaxies. The universe uses itself as a magnifying glass. Light doesn't lie. It shows us everything, even things we're not supposed to see. You've probably heard that light is energy, but it's more precise than that. Light is electromagnetic radiation, oscillating electric and magnetic fields rippling through space. Visible light is just one tiny slice of the electromagnetic spectrum. Radio waves are light you can't see. Microwaves are light your phone uses. Infrared is light you feel as heat. Ultraviolet is light that burns your skin. X-rays are light that passes through your body. Gamma rays are light born from exploding stars. All of it the same phenomenon. Different wavelengths, different energies, same essence. Your body knows how to read light even when you're not looking. Deep inside your brain, the suprachiasmatic nucleus tracks the rise and fall of daylight. It synchronizes your circadian rhythm, your internal 24-hour clock. When blue light hits your retina in the morning, your brain suppresses melatonin. You feel awake. When darkness falls, melatonin floods your system. You feel sleepy. This rhythm is older than humanity. It's written into the biology of nearly every living thing. Even bacteria respond to light. Even single-celled organisms without eyes can sense when day turns to night. Light doesn't age. A photon emitted at the beginning of the universe hasn't experienced a single moment of time. From light's perspective, the journey from emission to absorption is instantaneous. Time doesn't pass when you move at light speed. Einstein's equations show this clearly. A photon exists in a timeless state, connecting two moments, one when it's born, one when it's absorbed with no duration in between. You could say light lives in a single eternal instant. Plants understood this long before humans did. Chlorophyll molecules inside leaves capture photons and convert them into chemical energy through photosynthesis. 6 molecules of carbon dioxide, 6 molecules of water, light energy. The result, glucose and oxygen. The oxygen you breathe right now came from plants splitting water, molecules using nothing but sunlight. Every breath you take is a gift from light. Photosynthesis powers nearly all life on Earth. Food chains start with plants. Plants start with light. Even carnivores are eating sunlight, just 2 or 3 steps removed. Scientists estimate that photosynthesis converts around 100 terawatts of solar energy into chemical energy every year. That's 6 times more energy than all of human civilization uses. Nature is efficient in ways we're still learning to imitate. Light can heal. In the 1980s, researchers discovered that certain wavelengths of light could reduce inflammation and accelerate wound healing. Today, LED therapy treats skin conditions, chronic pain, even depression. Red and near-infrared light penetrate deep into tissue-boosting cellular energy production. Mitochondria, the powerhouses of your cells, absorb that light and produce more ATP, the molecule that fuels almost every process in your body. Light doesn't just show you the world, it repairs it. Some materials glow when you shine light on them. This is called fluorescence. Electrons absorb photons, jump to higher energy levels, then fall back down, releasing light of a different color. Jellyfish do this. Their bodies contain a protein called green fluorescent protein, or GFP. Scientists extracted GFP and learned to attach it to other proteins, making them glow under ultraviolet light. Now, researchers can watch individual molecules move inside living cells. They can see neurons firing in real time. They can track cancer cells as they spread. A glowing jellyfish changed biology forever. Light carries information. Fiber optic cables transmit data using pulses of light traveling through glass thinner than a human hair. The internet runs on light. Your voice during a phone call gets converted into light, sent across continents in milliseconds, then converted back into sound. Light doesn't get tired. It doesn't lose its clarity over distance the way electricity does in copper wires. Right now, light is carrying this story to you. You don't need to hold on to any of this. Let it wash over you. Light does the same. It touches everything without clinging. Your eyes evolved to catch photons. 3 types of cone cells live inside your retina, each tuned to different wavelengths. Short cones detect blue light around 420 nanometers. Medium cones capture green around 530 nanometers. Long cones respond to red near 560 nanometers. These three ranges combine to create every color you've ever perceived, millions of shades from just three sensors. But you're not seeing reality, you're seeing an interpretation. Mantis shrimp have 16 types of color receptors. They perceive wavelengths humans can't imagine, ultraviolet polarized light depths of color we have no words for. Research published in Science Journal shows they process color differently than expected, likely using their receptors for speed rather than precision. Light becomes a language only they can read fluently. Some people are tetrachromats. They have 4 types of cone cells instead of 3, mostly women. A genetic mutation on the X chromosome gives them an extra receptor, usually between red and green. Studies by Kimberly Jamison at UC Irvine suggest they can distinguish up to 100 million colors, while most humans max out around 1 million. A sunset you find beautiful might overwhelm them with shades you've never noticed. Your retina contains about 6 million cone cells and 120 million rod cells. Rods detect light intensity, but not color. They're concentrated around the edges of your retina, which is why faint stars become visible when you look slightly away from them. Astronomers call this averted vision. Your peripheral vision is more sensitive to dim light than your central gaze. Light doesn't always travel in straight lines through matter. When it enters water, it slows to about 225,000 kilometers per second, roughly 75% of its speed in vacuum. In glass, it slows even more to around 200,000 kilometers per second. This change in speed causes refraction, the bending of light at the boundary between materials. Willebrord Snellius described this mathematically in 1621. His law relates the angle of incidence to the angle of refraction based on the material's refractive indices. Rainbows are refraction made visible. Sunlight enters a raindrop, slows down, bends, reflects off the back surface, bends another time on the way out, and splits into its component wavelengths. Red bends least at about 42 degrees from the anti-solar point. Violet bends most at about 40 degrees. Each drop of water acts like a tiny prism. You see red on top because those drops are higher in the sky relative to your position. Someone standing next to you sees a slightly different rainbow. Their eyes catch light from different droplets. Every rainbow is personal. Double rainbows happen when light reflects twice inside each raindrop before exiting. The second arc appears fainter and reversed red on the inside, violet on the outside. The space between the two arcs looks darker than the rest of the sky. Photographers call this Alexander's band, named after Alexander of Aphrodisias, who described it around 200 AD. The phenomenon occurs because light between the two arcs gets redirected away from your eyes. It's a shadow in the sky made of redirected light. Moonbows exist too. They form at night when the moon is at least 50% full and less than 42 degrees above the horizon, with rain falling opposite the moon. The human eye struggles to see color in low light. Our cone cells need stronger signals, so moonbows often appear white or pale gray. But cameras with long exposures capture them in full color. Victoria Falls in Zambia and Yosemite Falls in California are famous moonbow locations. The light is there. Your eyes just can't translate it. Light remembers its journey. Polarization is the orientation of light's electromagnetic waves. Unpolarized light vibrates in all directions, perpendicular to its path. When light reflects off surfaces like water or glass at around 56 degrees, called Brewster's angle, it becomes partially polarized, oscillating mostly in one plane. Polarized sunglasses filter out horizontally polarized light-reducing glare. Edwin Land invented the first polarizing filter in 1928, while he was still a college student. He called it Polaroid. Your eyes can't detect polarization naturally, but some animals can. Bees use polarization patterns in the sky to navigate even on cloudy days. Octopuses and cuttlefish see polarized light and communicate with polarized patterns on their skin that only other cephalopods can see. Some birds use polarization to calibrate their magnetic compass during migration. Light holds secrets in its orientation. Sunlight takes 8 minutes and 20 seconds to reach Earth, but that's only the last leg of a much longer trip. Photons created in the sun's core through nuclear fusion don't escape immediately. The core is so dense, 150 times denser than water, that a photon might travel only a fraction of a millimeter before colliding with another particle. It gets absorbed and re-emitted millions of times. Scientists estimate it takes a photon anywhere from 10,000 to 170,000 years to random walk from the sun's center to its surface. Only then does it fly freely through space. The sunlight warming your face is older than human civilization. Light carries momentum despite having no mass. Photons carry momentum calculated as Planck's constant divided by their wavelength. When light hits a surface, it transfers that momentum. This creates radiation pressure. In 1873, James Clerk Maxwell predicted this effect. In 1901, Pyotr Lebedev measured it experimentally using a torsion balance in a vacuum. Solar sails use this principle. Japan's Ikero, a spacecraft launched in 2010, became the first to successfully demonstrate solar sail propulsion in deep space. The force is tiny, about 9 micronewtons per square meter, at Earth's distance from the sun. But in the vacuum of space with no friction, that gentle pressure builds velocity over time. One day light might carry us to other stars. Lasers are light that marches in step. Ordinary light sources emit photons randomly in all directions with mixed wavelengths. A laser produces coherent light, all photons vibrating in phase, traveling in the same direction with identical wavelengths. Theodore Maimon built the first working laser in 1960 using a ruby crystal. The word laser stands for light amplification by stimulated emission of radiation. Albert Einstein predicted stimulated emission in 1917, but it took 43 years to build a device that used it. Lasers measure distance to the moon within millimeters using retroreflectors left by Apollo astronauts. They cut through steel at industrial sites. They perform LASIK eye surgery by reshaping corneas with 193 nanometer ultraviolet light. They read data on Blu-ray discs using 405 nanometer blue-violet lasers, all because light learned to synchronize. Your pupils dilate and constrict to control how much light enters your eyes. In bright conditions, they shrink to about 2 millimeters in diameter. In darkness, they expand to around 8 millimeters. That's a 16-fold difference in area. The iris muscles respond to light intensity in less than a second through the pupillary light reflex, protecting your retina from damage while maximizing sensitivity in low light. But they also respond to emotion. Fear, surprise, attraction, all trigger pupil dilation through activation of the sympathetic nervous system. Eckhard Hess discovered in the 1960s that people unconsciously read each other's pupils during conversation. Dilated pupils can signal interest or arousal. Light reveals what you're feeling before you speak. Fireflies produce light through bioluminescence. Inside their abdomens, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase. The reaction releases energy as yellow-green light around 560 nanometers with almost no heat. Scientists call this cold light. Contrast that with incandescent bulbs, which waste 90% of their energy as heat. Fireflies achieve nearly 100% efficiency. Their bioluminescence has a quantum yield close to 0.88. Different species flash at different rates and patterns. Phoctinus pyralis males fly upward while flashing every 5.8 seconds at 25 degrees Celsius. Females perched in grass respond with a flash of their own about 2 seconds later. It's a conversation written in light. Some firefly species synchronize their flashes. In Southeast Asia, thousands of Pteroptyx males in a single mangrove tree pulse in perfect unison. Research by John and Elizabeth Buck in the 1960s showed each firefly adjusts its rhythm based on the flashes it sees nearby. Over time, the group locks into a shared tempo. It's emergence, no leader, no plan. Mathematical models suggest synchronization occurs when each firefly speeds up or slows down slightly in response to neighbors. Just light listening to light. Deep-sea creatures glow for different reasons. Below 200 meters, sunlight fades to nothing. About 90% of deep-sea animals produce bioluminescent light to attract mates, lure prey, or confuse predators. The anglerfish dangles a glowing lure, an esca created by symbiotic Vibrio bacteria. The hatchetfish has photophores on its belly that emit light matching the faint downwelling light from above, erasing its silhouette and making it invisible to predators below. This is called counter-illumination. Stephen Haddock's research documents over 700 genera that produce light. Light becomes camouflage in the deep. Some jellyfish glow when disturbed. Aquaria victoria emits blue-green light through a protein called equorin. When calcium ions flood its cells, triggered by physical disturbance, the protein glows. Osamu Shimomura isolated equorin in 1962. He and Roger Tsien later identified green fluorescent protein, or GFP, which converts the blue light to green. All three won the 2008 Nobel Prize in Chemistry. Scientists now insert GFP into other organisms. Mice glow green under UV light. Zebrafish with fluorescent organs. These tools let researchers track cells, measure neural activity, and watch diseases progress in real time. A jellyfish gave us a window into the living body. Light can trap atoms. In 1986, Stephen Chu and his team used intersecting laser beams to cool and hold sodium atoms in place. The technique is called optical molasses. Photons from the lasers hit atoms moving toward the light source, transferring momentum that slows the atoms down through the Doppler effect. When atoms are slowed to microkelvin temperatures, they hover in the intersection of laser beams. Chu shared the 1997 Nobel Prize in Physics for this work. Arthur Ashkin independently developed optical tweezers that use focused laser beams to trap microscopic particles. He won the 2018 Nobel Prize. Today, scientists use optical trapping to study quantum mechanics, measure piconewton forces, and manipulate individual DNA molecules. Light holds matter like hands holding water. You perceive brightness logarithmically, not linearly. A candle might produce 12 lumens of light. A 100-watt incandescent bulb produces about 1,600 lumens. That's over 130 times brighter, but it doesn't feel that way. Your eyes compress the range through neural adaptation. This logarithmic response is described by the Weber-Fechner law. Ernst Weber discovered in the 1830s that the smallest noticeable difference in stimulus intensity is proportional to the existing intensity. Gustav Fechner formalized this mathematically in 1860. A small increase in dim light feels like a big change, but the same absolute increase in bright light barely registers. Your brain is always adjusting the gain. Light doesn't need a medium. Sound requires molecules, air, water, solid matter, bumping into each other to propagate. But light is self-sustaining. An oscillating electric field creates a magnetic field perpendicular to it. The magnetic field creates an electric field. They leapfrog through empty space at constant speed. James Clerk Maxwell published his equations in 1865 describing how electricity and magnetism relate. When he calculated the speed of electromagnetic waves, he got approximately 310,000 kilometers per second, suspiciously close to the measured speed of light. He realized light was an electromagnetic wave. Suddenly, electricity, magnetism, and optics unified into a single theory. Heinrich Hertz confirmed Maxwell's prediction in 1887 by generating and detecting radio waves. Light is electricity and magnetism dancing through the void. Your skin can sense light without your eyes. Melanopsin, a photopigment discovered in 1998 by Inácio Provencio, exists in specialized retinal ganglion cells that don't contribute to vision. but regulate circadian rhythms. These same cells connect directly to the suprachiasmatic nucleus in your hypothalamus. Russell Foster's research at Oxford showed that even blind people with no conscious light perception can still synchronize their body clocks to day-night cycles if these cells remain functional. Light reaches deeper than sight. Plants sense light through photoreceptors too. Phytochromes detect red and far red light, triggering responses like germination and flowering. Cryptochromes respond to blue light, controlling stem elongation and leaf expansion. Phototropins also sense blue light, directing leaves and stems to grow toward light sources. Charles Darwin and his son Francis documented phototropism in 1880, showing that seedlings bend toward light because cells on the shaded side elongate faster. The plant doesn't want to reach the light. It just grows asymmetrically in response to photon gradients. Light bends time in ways you can measure. In 1971, Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners. The clocks that flew eastward, moving faster relative to Earth's rotation, lost 59 nanoseconds compared to clocks on the ground. The westward clocks gained 273 nanoseconds. Einstein's theory of relativity predicted both effects. Velocity slows time, and weaker gravity at altitude speeds it up. Light's constant speed creates a universe where time itself is flexible. GPS satellites account for relativity every day. They orbit at 20 to 200 kilometers altitude, traveling at 14,000 kilometers per hour. At that speed, special relativity predicts their clocks should run slower by about 7 microseconds per day. But at that altitude, gravity is weaker, so general relativity predicts their clocks should run faster by about 45 microseconds per day. The net effect satellite clocks gain 38 microseconds daily. Without correction, GPS would drift by 10 kilometers per day. Engineers program satellites to tick slower on purpose, so they stay synchronized with Earth-based clocks. Light shaped the first eyes. Around 540 million years ago, during the Cambrian explosion, the first primitive eyes appeared in the fossil record. Trilobites had compound eyes made of calcite crystals, literally rock for lenses. Andrew Parker proposed the light switch hypothesis in 2003, suggesting that the evolution of vision triggered an evolutionary arms race. Predators could see prey. Prey needed better camouflage or speed. Body plans diversified rapidly. Light didn't just illuminate the world, it redesigned it. Your cornea and lens focus light, but they do it differently. The cornea, the clear front surface of your eye, provides about 2/3 of your eye's focusing power, roughly 43 diopters. It's fixed in shape. The lens behind it contributes the remaining third and can change shape through accommodation. Tiny ciliary muscles contract to make the lens thicker for near vision, relaxing to flatten it for distance. This ability declines with age. By your mid-40s, the lens loses elasticity. You develop presbyopia, reading glasses become necessary. Light demands flexibility, and time takes it away. Some animals see light you can't. Bees perceive ultraviolet light down to about 300 nanometers. Many flowers have ultraviolet patterns invisible to humans, but vivid to pollinators. What looks like a plain yellow flower to you might display bold nectar guides to a bee runways pointing toward pollen. Carl von Frisch demonstrated this in 1914 by training bees to feed from dishes marked with UV reflecting versus UV absorbing papers. Plants and pollinators co-evolved a secret language written in wavelengths. Reindeer can see ultraviolet light too. Research published in 2011 by Glenn Jeffrey showed that reindeer retinas detect UV down to 310 nanometers. In Arctic winters, snow reflects UV strongly, while objects like lichen and urine absorb it, appearing dark to UV-sensitive eyes. This helps reindeer find food and detect predators against white landscapes. Light adapts to environments and eyes follow. Infrared light carries heat. You can't see it, but you feel it. Wavelengths longer than 700 nanometers transfer energy directly to molecules, causing them to vibrate faster. That's heat. Pit vipers have specialized organs between their eyes and nostrils that detect infrared radiation. They sense the body heat of warm-blooded prey in total darkness. The membrane in the pit contains thermoreceptors sensitive to temperature changes as small as 0.003 degrees Fahrenheit. A mouse 40 centimeters away radiates enough infrared for a rattlesnake to strike with precision. Your body radiates infrared light constantly. At normal body temperature 37 degrees or 310 Kelvin, you emit peak radiation around 9/300 nanometers, according to Wien's displacement law. That's deep in the infrared. Thermal cameras detect this emission. You glow in the dark to anything with the right sensors. Roughly 100 watts of power radiate from your body as infrared light, the same as a bright incandescent bulb. You're always shining. Light can stop. In 1999, Line Hao and her team at Harvard slowed light to 17 meters per second, about 38 miles per hour, by passing it through a Bose-Einstein condensate of ultra-cold sodium atoms. In 2001, they stopped light completely storing its quantum state in atomic spins for about a millisecond before releasing it. The photons disappeared and reappeared unchanged. Light, which normally refuses to stand frozen, learned to wait. Shadows move faster than light. It sounds impossible, but it's true. Shine a laser pointer at the moon and sweep your hand across the beam. Your shadow on the lunar surface moves at many times the speed of light, hundreds of thousands of kilometers per second. But no information travels that fast. No matter, no energy. The shadow isn't a thing. It's the absence of a thing. Physics allows shadows and spots of light to move faster than light because they don't carry causality. Eclipses prove the moon's distance. During a total solar eclipse, the moon's disk covers the sun almost exactly. The sun's diameter is about 400 times larger than the moon's, but it's also about 400 times farther away. This coincidence makes total eclipses possible. Aristarchus of Samos estimated distances using eclipse geometry around 270 BC. He got the ratios roughly correct, but underestimated absolute distances. Modern measurements put the sun at 149.6 million kilometers and the moon at 384,400 kilometers on average. Light takes 1.28 seconds to reach the moon. The sun's surface temperature is about 5,800 Kelvin. At that temperature, it emits peak radiation around 500 nanometers green light. But your eyes perceive the sun as white or yellow, not green. That's because the sun emits light across the entire visible spectrum, not just at the peak wavelength. Your brain integrates all wavelengths, and the combined signal appears white. Earth's atmosphere scatters shorter blue wavelengths more than longer red wavelengths, Rayleigh scattering, which makes the sky blue and sunsets orange. The light doesn't change color. The path through air changes what reaches you. Auroras form when charged particles from the solar wind collide with Earth's atmosphere. Electrons and protons trapped in the magnetosphere spiral down toward the poles along magnetic field lines. When they hit oxygen atoms at altitudes around 200 to 300 kilometers, they excite electrons in those atoms to higher energy states. The electrons fall back down, releasing green light at 557.7 nanometers. At higher altitudes above 300 kilometers, oxygen emits red light at 630 nanometers. Nitrogen produces blue and purple hues. Christian Birkeland proposed in 1908 that auroras were caused by electrons from the sun, though it took decades to confirm. You can see individual photons. In 1942, Zelig Hecht and his colleagues calculated that human rod cells can detect a single photon. Later experiments confirmed this. Under ideal conditions, completely dark adapted eyes looking slightly off-center to engage rod-rich peripheral vision your retina can respond to as few as 5 to 7 photons reaching it. Not all reach your conscious awareness because neural noise filters out weak signals, but the physical detection happens. Your eyes are sensitive enough to catch the faintest whispers of light. Color blindness affects how you decode light. About 8% of men and 0.5% of women of Northern European descent have red-green color blindness caused by mutations in the genes encoding red or green cone pigments on the X chromosome. John Dalton described his own color blindness in 1794. He saw red as dim and confused reds with greens. Protanopia means missing red cones. Deuteranopia means missing green cones. Tritanopia, missing blue cones, is rarer, affecting about 1 in 10,000 people. Each variation changes how light becomes experienced. Sunlight powers Earth's weather. The sun delivers about 1,361 watts per square meter to the top of Earth's atmosphere, a value called the solar constant. About 30% reflects back into space from clouds, ice, and atmospheric particles. The remaining 70% warms the surface and drives wind, rain, ocean currents, and storms. Hurricanes are heat engines powered by warm ocean water. Thunderstorms are convection cells lifting moist air. All of it traces back to light, from the sun turning into kinetic energy through temperature differences. You can hear light. Photoacoustic spectroscopy uses pulses of light to heat materials, causing them to expand rapidly and produce sound waves. Alexander Graham Bell invented the photophone in 1880, transmitting voice signals on a beam of light. The device used a vibrating mirror modulated by sound to encode audio onto reflected sunlight. A selenium cell at the receiving end detected intensity changes and converted them back to sound. Bell considered it his greatest invention, greater than the telephone. Light became voice. Light erases itself through interference. When two light waves meet, they can add together or cancel out depending on their phase relationship. Thomas Young demonstrated this in 1801 with his double-slit experiment. Light passing through two narrow slits creates an interference pattern of bright and dark bands on a screen. Bright bands form where waves arrive in phase peaks aligning with peaks. Dark bands form where waves arrive out of phase peaks meeting troughs. The dark bands aren't shadows. They're places where light plus light equals darkness. Photography captures light by chemistry. Silver halide crystals in film react when struck by photons. The energy breaks silver ions, free-forming metallic silver atoms. These form a latent image invisible until developed. Louis Daguerre announced the daguerreotype process in 1839, creating permanent images on silver-coated copper plates. Modern digital cameras use silicon photodiodes instead. Photons knock electrons loose, creating electrical current measured by pixels. Either way, light leaves its mark by giving energy to matter. Light knows no fatigue. A photon emitted by a star 13 billion years ago arrives at your telescope with its energy and wavelength intact, only shifted by the universe's expansion. It crossed incomprehensible distances without decay. Light doesn't age or fade unless something absorbs it or stretches its wavelength. The cosmic microwave background radiation, photons from 380,000 years after the Big Bang, still fills space today, cooled to 2.7 Kelvin, but structurally unchanged. Light remembers its beginning. Diamonds scatter light into rainbows. When white light enters a diamond, it slows to about 124,000 kilometers per second, 41% of its vacuum speed. The diamond's refractive index of 2.417 is one of the highest among transparent materials. This extreme slowing causes severe refraction and dispersion, splitting white light into its component colors. The diamond's precise cut angles, calculated by Marcel Tolkowski in 1919, ensures light reflects internally multiple times before exiting, creating what jewelers call fire and brilliance. Light becomes trapped beauty. Your tears refract light differently than water. Tears have a refractive index of about 1.337, slightly lower than pure water at 1.333 because of dissolved proteins and lipids. When you cry, the thin tear film on your cornea changes how light enters your eye. Things might look blurred, not just from excess fluid, but from optical distortion. Ophthalmologists measure tear film stability by observing how quickly it breaks up. After a blink, normally 10 seconds or more, light reveals the chemistry of emotion. Mirages are real light phenomena, not hallucinations. On hot days, air near the ground heats up and becomes less dense than cooler air above. Light travels slightly faster through less dense air. When light from the sky travels downward at a shallow angle, it bends, refracts through the temperature gradient, and curves back upward before reaching the ground. Your brain interprets this bent light path as a reflection from water on the road. The mirage shows you real light from the sky, just delivered along an unexpected path. Gaspard Monge provided the first scientific explanation in 1799 during Napoleon's Egyptian campaign. Superior mirages happen in cold conditions. When air near the surface is colder than air above common over ice or cold ocean water, light bends downward. Objects below the horizon can appear elevated or inverted. Ships seem to float in the sky. Entire islands appear where none exist. The Fata Morgana, named after the sorceress Morgan Le Fay from Arthurian legend, creates complex layered mirages with castles and cliffs shimmering above the sea. Sailors reported these for centuries before understanding them. Light conjures phantom worlds. Glass is technically a liquid, sort of. It's an amorphous solid molecules, frozen in a disordered state like a liquid, but rigid like a solid. Medieval cathedral glass is sometimes thicker at the bottom, leading to myths that glass flows over centuries. Scientists now know this thickness variation came from manufacturing, not flow. Glass would take longer than the age of the universe to flow noticeably at room temperature. But light doesn't care about the molecular structure. It passes through glass, whether the atoms are crystalline or chaotic. Fiber optic cables carry light with minimal loss. Modern optical fibers made from ultra-pure silica glass lose only about 0.2 decibels per kilometer at 1,550 nanometer wavelength. That means light can travel 50 kilometers and retain about 1% of its original intensity. Charles Kao proposed using glass fibers for telecommunications in 1966, though glass at the time had too many impurities. He won the 2009 Nobel Prize in Physics after manufacturers achieved the necessary purity. Today, undersea cables carry 99% of intercontinental data as pulses of infrared light. Light makes clouds white. Water droplets in clouds are roughly 10 to 20 micrometers in diameter, larger than visible light wavelengths. When light hits these droplets, all wavelengths scatter roughly equally through a process called Mie scattering. Since all colors scatter together, the cloud appears white. Rain clouds look dark gray because they're so thick that little light penetrates through to your eyes. The darkness isn't the cloud's color. It's the absence of transmitted light. Your computer screen doesn't emit white light. It creates the illusion of white by combining red, green, and blue pixels called RGB color space. Each pixel contains 3 subpixels with different phosphors or LEDs. By varying the intensity of each subpixel, the screen produces millions of colors. The eye can't resolve individual subpixels from normal viewing distance, so your brain merges them into continuous color. White on a screen is just 3 colors shouting together. Isaac Newton proved in 1666 that white light contains all colors by using a prism to split sunlight, then a second prism to recombine the spectrum back into white. Sunset colors depend on dust and particles. Clean air produces pale orange sunsets. Volcanic eruptions inject sulfate aerosols into the stratosphere, creating vivid red sunsets visible worldwide for months. After Mount Pinatubo erupted in 1991, sunsets glowed dramatically for 2 years. Benjamin Franklin noticed unusually colored sunsets and a dry fog across Europe in 1783 after the Laki volcanic fissure erupted in Iceland, releasing 120 million tons of sulfur dioxide. Light becomes a messenger of distant catastrophes. Stars twinkle because of atmospheric turbulence. Air pockets with different temperatures and densities move constantly, causing starlight to refract erratically. The star's apparent position and brightness flicker several times per second. Planets twinkle less because they show a small disk rather than a point. The disk averages out turbulence fluctuations. Astronomers call this twinkling seeing. Observatories choose mountaintop locations with stable air. Adaptive optic systems developed in the 1990s use deformable mirrors to counteract atmospheric distortion in real-time sharpening images. Black holes trap light permanently. If you could approach a black hole, you'd see light orbiting at the photon sphere, a radius about 1.5 times the event horizon. Inside the event horizon, space-time curves so severely that all paths lead inward. Light emitted inside can never escape. The event horizon isn't a physical surface, but a mathematical boundary. Once light crosses it, the future always points toward the singularity. Stephen Hawking showed in 1974 that black holes emit radiation through quantum effects. But this is incredibly faint for stellar mass black holes. The first photograph of a black hole's shadow appeared in 2019. The Event Horizon Telescope, a network of radio dishes spanning the globe, imaged the supermassive black hole in galaxy M87. The black hole itself is invisible, but hot gas orbiting it emits radio waves. The image shows a bright ring, with a dark center, the shadow cast by the event horizon. The black hole contains 6.5 billion solar masses. The shadow is about 42 microarc seconds across, as seen from Earth, equivalent to seeing a grapefruit on the moon. Light drew the outline of something that captures light. Glitter works through specular reflection. Each flake of glitter has a flat metallic surface that reflects light like a tiny mirror. Unlike diffuse reflection, where rough surfaces scatter light in all directions, specular reflection sends light at a specific angle. When you move, glitter-different flakes catch the light and flash at you. The effect is sparkle. Henry Ruyschmann invented modern glitter in 1934 by developing a machine to cut thin sheets of plastic into tiny pieces. Light found a way to multiply itself across 1 million fragments. Soap bubbles show interference colors. The bubble wall is about 100 nanometers thick, comparable to visible light wavelengths. Light reflects from both the outer and inner surfaces. These reflections interfere with each other. Where they're in phase, the color intensifies. Where they're out of phase, the color cancels. Different thicknesses produce different colors. As the bubble drains and thins under gravity, colors shift red at the top, where it's thicker blue, and violet lower down. Just before popping the top, becomes so thin, around 25 nanometers, it appears black. Light reveals the invisible architecture of ephemeral things. Holograms record light's phase information. Normal photographs capture only intensity, how bright each point is. Holograms also record the phase, the specific position in each light wave's oscillation cycle. Dennis Gabor invented holography in 1947 while trying to improve electron microscopes. A hologram is made by splitting a laser beam. One part, the reference beam, hits the photographic plate directly. The other part reflects off the object. First then hits the plate. The interference pattern between these beams encodes both intensity and phase. When you illuminate the hologram with the same wavelength, it reconstructs the original light field. You see depth, parallax, 3 dimensions. Light teaches itself to remember shape. Gravitational waves stretch light. When LIGO detected gravitational waves in 2015, it measured the stretching and squeezing of space itself. Each detector uses laser interferometry, splitting a laser beam and sending it down two perpendicular 4-kilometer arms. Mirrors at the ends reflect the light back. Normally, the beams return in phase and cancel out. But when a gravitational wave passes, it stretches one arm and compresses the other by about 1/10,000th the diameter of a proton. This tiny difference creates an interference pattern. Light becomes the ruler that measures ripples in space-time. Your shadow has no weight or substance. It's not a thing, but the absence of light. Democritus understood this in ancient Greece around 400 BC. He described shadows as regions where light corpuscles can't reach, because an object blocks their path. He was fundamentally correct, though we now understand light is waves and particles. Shadows contain no matter, carry no energy, exert no force. Yet they convey information. Your shadow's shape tells observers about your form. Light defines objects by what it can't reach. Light pressure can levitate small particles. Optical levitation uses tightly focused laser beams to trap and suspend microscopic objects, dust particles, droplets, even individual atoms. The radiation pressure from photons hitting the particle from below balances gravity. Arthur Ashkin pioneered optical tweezers in the 1980s. He trapped viruses, bacteria, and organelles without touching them. In 2018, at age 96, he won the Nobel Prize in Physics, becoming the oldest Nobel laureate ever. Light learned to hold life itself without harm. Caustics are patterns light makes when reflected or refracted by curved surfaces. The bright lines at the bottom of a swimming pool are caustic sunlight, focused by rippling water. The edge of your coffee cup casts caustic patterns on the table when light refracts through the curved meniscus. René Descartes analyzed caustics mathematically in 1637 while explaining rainbows. The bright arc of a rainbow is itself a caustic, a place where refracted light rays concentrate. Light gathers in intensity where geometry directs it. You can weigh light. A photon has no rest mass, but it carries energy, and energy has mass equivalence through Einstein's E1mc2. A photon's relativistic mass equals its energy divided by C2. A green photon with a wavelength of 500 nanometers carries about 4 Gies-10^19 joules of energy. Divide by C2 and you get an effective mass of about 4.4 x 1036 kilograms. It's fantastically small but real. A mole of green photons would weigh 2.7 nanograms. Light has weight when it carries energy. Cherenkov radiation glows blue in nuclear reactors. When charged particles travel through water faster than light, travels through water which is 75% of light's vacuum speed, they emit a blue glow. It's the optical equivalent of a sonic boom. Pavel Cherenkov observed this in 1934. The effect happens because particles disturb the electromagnetic field faster than light, can propagate the disturbance through the medium, creating shock waves of photons. The glow doesn't mean anything travel faster than vacuum light speed, just faster than light in that specific medium. Still, it's eerie. Light from motion, not heat or chemistry. Light connects moments. The photon touching your face left the sun 8 minutes ago. If the sun vanished, you'd see it shining for 8 more minutes before darkness arrived. You'd feel gravity for those same 8 minutes. Gravitational effects also travel at light speed. The universe wouldn't inform you instantly. Light's finite speed creates a delay, a buffer between events and knowledge. Everything you see happens slightly in the past. The farther you look, the older the information. You live in a present made from ancient light. Prisms taught Newton that color lives inside white light. In 1666, during an outbreak of plague, he conducted experiments in his room at Woolsthorpe Manor. He let sunlight pass through a triangular glass prism, expecting a circular white spot with colored edges. Instead, the spectrum stretched into an oblong rainbow. He called the colors red, orange, yellow, green, blue, indigo, and violet 7 colors to match the 7 notes of the musical scale, though indigo is barely distinguishable to most eyes. When he passed that spectrum through a second inverted prism, the colors recombined into white light. Color wasn't added by the glass. It was separated from light that always contained it. Your brain invents magenta. Look at a color wheel, and you'll see red transitioning through orange, yellow, green, cyan, blue, and violet before returning to red. But magenta, the color between violet and red, doesn't exist in the spectrum. It has no single wavelength. Your brain creates magenta when red and blue cones fire simultaneously without green activation. It's an extraspectral color, a fabrication to fill the gap where the spectrum loops back on itself. Magenta is proof that color is as much about neural processing as physics. Bioluminescent waves glow blue at night. Dinoflagellates, single-celled algae containing luciferin and luciferase, emit light when disturbed by motion. Their bioluminescence serves as a defense mechanism, startling predators or attracting larger predators to eat the grazers. Tourist beaches in the Maldives, Puerto Rico's Mosquito Bay, and California's Torrey Pines sometimes glow electric blue when waves break or swimmers move through the water. Each dinoflagellate produces light for only 1/10 of a second, but millions together create sustained glow. Light becomes a living warning system. Glow-in-the-dark materials store light energy. Phosphorescent substances like zinc sulfide or strontium illuminate absorbed photons, exciting electrons to higher energy states. Unlike fluorescence, which releases light immediately, phosphorescence traps electrons in metastable states. They slowly fall back to ground states over minutes or hours, emitting green or blue photons gradually. The process is temperature dependent. Warmer materials glow brighter but fade faster. Colder materials glow dimmer but last longer. Clock faces. Emergency exit signs and children's toys use phosphorescence. Light borrows time. The Mpemba effect suggests hot water can freeze faster than cold water under certain conditions, though scientists debate the exact mechanism. One hypothesis involves evaporation. Hot water loses mass faster, leaving less water to freeze. Another points to convection currents organizing differently in hot versus cold water, affecting how heat transfers to the freezer walls. Light doesn't directly cause this, but it relates to how energy moves through systems. Aristotle noticed the phenomenon around 350 BC. Tanzanian student Erasto Mpemba rediscovered it in 1963 while making ice cream. Sometimes the path to cold runs through heat. Polarized light reveals stress in transparent materials. When you place clear plastic between crossed polarizing filters and shine light through colorful patterns emerge where the plastic is stressed or bent. The stress creates birefringence, different refractive indices in different directions. Light polarized in one direction travels at a different speed than light polarized perpendicular to it. This creates phase differences that show up as colors when the light reaches the second polarizer. Engineers use photoelasticity to visualize stress in architectural models and mechanical parts. Light makes invisible forces visible. Sundogs appear as bright spots on either side of the sun. They form when sunlight refracts through hexagonal ice crystals in high cirrus clouds. The crystals act like prisms, bending light by 22 degrees. When the crystals are plate-shaped and floating horizontally, they create two bright spots, parhelia, flanking the sun at the same altitude. Often they show red on the side nearest the sun and blue on the outer edge. Aristotle described sundogs in Meteorologica around 340 BC. Sailors consider them omens. Light paints symmetry in ice. Snell's law predicts exactly how light bends. When light travels from one medium to another, the ratio of the sine of the angle of incidence to the sine of the angle of refraction equals the ratio of the two media's refractive indices. Mathematically, n1 sin Th1 r n2 sin T2. Willebrord Snellius discovered this in 1621, though Ibn Sahl described it in Mesopotamia around 984 AD. The law works because light takes the path requiring the least time, Fermat's principle of least time, formulated in 1662. Light is efficient. Total internal reflection traps light inside materials. When light tries to exit a dense medium like glass or water into a less dense medium like air, it can reflect entirely back if the angle is too steep. The critical angle for water is about 48.6 degrees from the normal. Fiber optic cables exploit this light, bounces down the cable's core, never escaping into the cladding. Fish underwater looking up see a circular window to the sky. Outside that window, called Snell's window, they see only reflections of the water around them. Divers experience the reverse looking up. They see a compressed view of the entire surface world squeezed into a cone. Light makes borders. Lightning produces light through plasma. When electrical potential between clouds and ground exceeds the air's dielectric breakdown, about 3 million volts per meter, electrons flow rapidly, heating air to 30,000 Kelvin, 5 times hotter than the sun's surface. At these temperatures, air molecules ionize into plasma, emitting intense white-blue light. The lightning channel is only 2 to 3 centimeters wide, but carries currents up to 200,000 amperes. Light reaches your eyes almost instantly. Thunder, the sound of superheated air expanding explosively, arrives later. Count the seconds, divide by 5, and you know the distance in miles. Light outpaces its own announcement. Neon signs work through electrical discharge. A glass tube filled with low-pressure neon gas has electrodes at both ends. Apply high voltage around 15,000 volts, and electrons accelerate through the gas, colliding with neon atoms. These collisions excite electrons in the neon atoms to higher energy levels. When they fall back, they emit photons. Neon produces red-orange light around 650 nanometers. Other gases produce different colors. Argon gives lavender helium, gives yellow mercury vapor, gives blue. Mix gases or use phosphor coatings, and you can create nearly any color. Georges Claude demonstrated the first neon lamp in Paris in 1910. Light became advertisement. Luminol glows blue when it contacts blood. Forensic investigators spray luminol solution, a mixture of luminol, hydrogen peroxide, and a hydroxide on surfaces. If iron from hemoglobin is present, it catalyzes a reaction that produces an excited state molecule. When this molecule relaxes, it emits blue chemiluminescence around 425 nanometers. The glow lasts about 30 seconds. Luminol can detect blood diluted to 1 part per million, even after attempts to clean it. The reaction is so sensitive it sometimes gives false positives from bleached copper or horseradish. Light speaks chemistry's secrets. Laser cooling slows atoms close to absolute zero. When atoms move toward a laser beam, tuned slightly below an absorption frequency, the Doppler effect shifts the light into resonance. The atom absorbs a photon, gaining momentum in the direction opposite its motion, slowing down. The atom then re-emits the photon in a random direction. On average, many absorption-emission cycles remove kinetic energy from the atom. In 1995, Eric Cornell and Carl Wieman used this technique to cool rubidium atoms to 170 nanokelvin, creating the first Bose-Einstein condensate. At these temperatures, quantum effects dominate. Atoms lose individuality and behave as a single quantum entity. Light makes matter surrender to stillness. Quantum entanglement links photons across distance. When 2 photons are created in certain ways, their properties become correlated. Measure the polarization of one photon, and you instantly know the polarization of the other, even if they're separated by kilometers. Einstein called this spooky action at a distance, and believed it proved quantum mechanics was incomplete. But experiments by Alain Aspect in 1982 confirmed entanglement is real. The photons don't communicate, there's no signal traveling between them. The correlation is built into their quantum state from creation. In 2017, Chinese researchers entangled photons between a satellite and ground stations 100-200 kilometers apart. Light defies separation. Your smartphone camera sees infrared. Digital sensors respond to wavelengths from about 350 to 100 nanometers. The human eye stops at 700 nanometers, but silicon photodiodes keep detecting into the near-infrared. Manufacturers install infrared blocking filters over camera sensors to make photos look natural, but TV remote controls emit infrared around 940 nanometers. Point one at your camera and press a button. You'll see it flash on the screen, even though your eyes see nothing. Light has colors your body can't translate without help. The cosmic microwave background is ancient light stretched into microwaves. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. Before this recombination, the universe was opaque. Photons scattered constantly off free electrons. After recombination, photons could travel freely. This surface of last scattering is the oldest light we can see. It was emitted at a temperature of 3,000 Kelvin warm red light. But cosmic expansion has stretched those photons by a factor of about 1/100, shifting them into microwave wavelengths. Today, the CMB has a temperature of 2.725 Kelvin. Arno Penzias and Robert Wilson discovered it accidentally in 1964, thinking it was noise in their radio antenna. They won the 1978 Nobel Prize. Light carries the universe's baby picture. Gravitational lensing bends light around massive objects. Einstein's general relativity predicts that mass warps space-time and light follows the curvature. In 1979, astronomers discovered the twin quasar, two identical images of the same distant quasar created by a galaxy between us and it, acting as a gravitational lens. The galaxy's gravity bent light from the quasar around both sides, creating double images. Since then, astronomers have found thousands of gravitational lenses. Some create Einstein rings, complete circles of light. The most extreme lenses magnify distant galaxies, allowing us to see objects too faint to detect otherwise. Light submits to gravity's geometry. Laser guide stars help telescopes see clearly. High-altitude turbulence blurs astronomical images. Adaptive optics systems correct this by measuring the distortion and adjusting a deformable mirror in real time. But this requires a bright reference star near the target. If no natural star exists, astronomers create an artificial one. A powerful sodium laser tuned to 589 nanometers excites sodium atoms in the mesosphere at 90 kilometers altitude. These atoms glow, creating a point of orange light that acts as a guide star. W.M. Keck Observatory in Hawaii and the Very Large Telescope in Chile use this technique. Light makes its own reference point. Slow glass is science fiction, but fascinating. Bob Shaw's 1966 short story, Light of Other Days, imagine glass so dense that light takes years to pass through it. You could buy a pane that spent a decade facing a beautiful meadow, then install it in your window to watch that meadow for another decade. It's impossible with known physics. Light always moves at CIN through a medium with refractive index n. But the idea captures something true about light. It connects moments separated by time. Every photon carries history. Ancient astronomers measured Earth using shadows and sunlight. Around 240 BC, Eratosthenes noticed that at noon, on the summer solstice in Syene, Egypt, the sun shone straight down a well with no shadow. The same day in Alexandria, 800 kilometers north, a vertical stick cast a shadow at about 7.2 degrees from vertical. He realized Earth must be curved. Using geometry, he calculated Earth's circumference at roughly 40,000 kilometers, remarkably close to the modern value of 40,075 kilometers at the equator. Light traveling in straight lines revealed the planet's shape. Sundials were humanity's first precise clocks. A gnomon, a vertical stick, or a triangular blade casts a shadow that moves as the sun travels across the sky. Ancient Egyptians used obelisks as gnomons around 3500 BC. The shadow's length and direction indicated time of day. But sundials have quirks. They show solar time, not clock time. Earth's elliptical orbit and axial tilt cause the sun to run fast or slow by up to 16 minutes throughout the year, an effect called the equation of time. Sundials told humans that even celestial motion has irregularities. Your circadian clock responds to blue light specifically, melanopsin. The photopigment in intrinsically photosensitive retinal ganglion cells peaks in sensitivity around 480 nanometers blue light. This is why blue-enriched light from screens before bed disrupts sleep. Studies show that exposure to bright blue light in the evening suppresses melatonin production by up to 50%. Amber or red light has minimal effect because melanopsin barely responds to those wavelengths. Harvard researchers found that reading on a light-emitting device before bed delayed melatonin onset by about 1.5 hours compared to reading a printed book. Light hijacks your sense of time. Seasonal affective disorder correlates with reduced light exposure. During winter months, at high latitudes, daylight shrinks to 6 hours or less. Some people develop depression lethargy and increased sleep. The condition affects about 5% of Americans, more common in women and northern states. Light therapy using 10,000 lux bright white light for 30 minutes each morning can alleviate symptoms in about 60 to 80% of cases. Norman Rosenthal and his team at NIMH first described SAD systematically in 1984. The mechanism likely involves both circadian disruption and serotonin regulation. Light stabilizes mood. Vitamin D synthesis requires ultraviolet B light. When UVB photons with wavelengths between 290 and 315 nanometers hit your skin, they convert 7-dehydrocholesterol into pre-vitamin D3. Body heat then converts this into vitamin D3, which the liver and kidneys transform into active calcitriol. Fair-skinned people can produce about 10,000 into 25,000 IU of vitamin D from 15 minutes of noon summer sun exposure on arms and legs. Darker skin requires longer exposure due to melanin absorbing UV. Vitamin D deficiency affects over 1 billion people worldwide. Glass windows block UVB, so indoor light doesn't help. Light builds your bones. The sun's spectrum includes invisible threats. Ultraviolet C 100, 280 in emitters is completely absorbed by Earth's ozone layer. UVB 280s, 315 nanometer, causes sunburn and DNA damage, leading to skin cancer. UVA 315 to 400 nanometer penetrates deeper, causing aging and contributing to melanoma. The UV index developed by Canadian scientists in 1992 rates daily UV radiation levels from 0 to 11 plus. An index of 10 means fair skin can burn in about 10 to 15 minutes. Sunscreen with SPF 30 blocks about 97% of UVB. SPF 50 blocks 98%. The difference is small but cumulatively protective. Light carries danger in wavelengths you don't see. Phototherapy treats jaundice in newborns. When babies accumulate bilirubin, a yellow pigment from breaking down red blood cells, their skin turns yellow. High levels can cause brain damage. Blue light around 460 to 490 nanometers breaks down bilirubin into water-soluble forms the baby can excrete. Hospitals use Biley lights or phototherapy blankets. The treatment was discovered accidentally in 1956 when a nurse in Essex, England, noticed that jaundiced babies near windows recovered faster than those in darker areas. Sunlight through glass was treating them. Light heals by transformation. Lasers can start nuclear fusion. At the National Ignition Facility in California, 192 high-powered lasers converge on a tiny capsule of hydrogen isotopes, deuterium and tritium. The lasers deliver about 2.05 megajoules of energy in a few nanoseconds, compressing and heating the fuel to 100 million degrees Celsius. Under these conditions, hydrogen nuclei overcome electrostatic repulsion and fuse, releasing energy. In December 2022, NIF achieved net energy gain, more energy out than the lasers delivered to the target. Light became the spark for the same reaction that powers stars. Photons have no electric charge, yet they mediate electromagnetic force. In quantum electrodynamics, when two electrons repel each other, they exchange virtual photons. These aren't photons. You can see they exist only during the interaction, popping in and out of existence within the limits of Heisenberg's uncertainty principle. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed QED in the 1940s. Feynman diagrams visualize these interactions, wavy lines representing photons connecting straight lines representing electrons. Light holds the universe together at quantum scales. Cameras measure exposure using light meters. Early photographers used extinction meters. You looked through the device until you could just see an image with the brightness determining exposure. Modern cameras use silicon photodiodes that generate current proportional to light intensity. The camera measures light in exposure value EV, where EV0 equals 1 second at f1.0. Each EV increment represents a doubling of light. Your eye can adapt to lighting variations over about 20 EV, a range of 1 million to 1, but a camera sensor captures only about 10 to 14 EV in a single shot. Photographers bracket exposures or use HDR to extend this range. Light exceeds the machine's capacity. Lightning is 5 times hotter than the sun's surface, but it doesn't melt everything it strikes. The heat duration matters. Lightning lasts only 1 to 2 milliseconds. In that brief moment, objects can heat to extreme temperatures, but there's not enough time for heat to conduct deeply into materials. This is why people can survive lightning strikes. The current often flashes over the skin's surface rather than traveling through the body, a phenomenon called external flashover. About 90% of lightning strike victims survive, though many suffer long-term neurological effects. Light and electricity siblings in violence. The speed of light in vacuum is exactly 299,792,458 meters per second. By definition since 1983. Before then, scientists measured it with increasing precision. Galileo tried in 1638 using lanterns and hilltops. He failed because human reaction time is too slow. Ole Roemer succeeded in 1676 by observing Jupiter's moon, Io. He noticed its eclipses behind Jupiter occurred later, when Earth was farther from Jupiter. Light took longer to reach Earth, proving it traveled at finite speed. Albert Michelson measured light speed to high precision in 1926 using rotating mirrors, earning the first American Nobel Prize in Science. Light speed defines the meter, the distance light travels in, 1,299,792,458 of a second. Quantum tunneling allows light to pass through barriers. If you place 2 prisms close together with a small air gap, light undergoes total internal reflection. At the first prism-air interface, classically, no light should reach the second prism. But quantum mechanics permits a small probability that photons tunnel across the gap. This is called frustrated total internal reflection. The effect is observable when the gap is smaller than the light's wavelength. It's used in optical switches and couplers. Light finds paths where classical physics says none exist. Metamaterials bend light in unnatural ways. Normal materials have positive refractive indices. Light bends one way when entering. Metamaterials engineered with structures smaller than light's wavelength can have negative refractive indices. Light bends the opposite direction. In 2006, David Smith and colleagues created a microwave cloak using metamaterials that guided waves around an object. Visible light cloaking remains limited to tiny objects and narrow wavelength ranges, but the principle works. Light can be taught to flow around obstacles like water around a stone. Raman scattering changes light's energy. When light hits molecules, most photons scatter elastically, same energy, different direction. But a small fraction, about 1 in 10 million, scatters inelastically. The photon gives energy to the molecule, exciting molecular vibrations, and emerges with lower energy and longer wavelength. This is Raman scattering, discovered by C.V. Raman in 1928. He won the Nobel Prize in 1930. Raman spectroscopy uses this effect to identify molecules. Each molecule has a unique vibrational fingerprint. Light becomes a probe of molecular identity. Your eyes adapt to darkness through rhodopsin regeneration. In bright light, rhodopsin, the light-sensitive protein in rod cells, breaks down into retinol and opsin. This process, called bleaching, makes rods insensitive. In darkness, enzymes slowly regenerate rhodopsin over 20 to 40 minutes. That's why you can't see when you first enter a dark room, but gradually adapt. Cone cells adapt faster in 5 to 10 minutes. Vitamin A is essential for retinal synthesis, which is why vitamin A deficiency causes night blindness. Pirates supposedly wore eye patches to keep one eye dark adapted for fighting below deck. Light demands preparation. Zodiacal light is sunlight scattered by interplanetary dust. After sunset or before sunrise in dark locations, you might see a faint triangular glow along the ecliptic, the plane of the solar system. Ancient astronomers noticed it. Giovanni Cassini correctly identified the cause in 1683. The dust particles are tiny micrometers in diameter remnants of asteroids and comets. They scatter sunlight most efficiently when the sun is just below the horizon. The dust fills the inner solar system, forming a flat disk. Every planet moves through this shared cloud. Light makes the invisible suburbs of the solar system briefly visible. Your body temperature radiates light constantly. Wien's displacement law states that peak emission wavelength equals 2,897 micrometers divided by temperature in Kelvin. At 310 K, your body peaks around 9.3 micrometers thermal infrared. Night vision goggles detect this emission. Predators like pit vipers use infrared to hunt. On a cold night, you're the brightest thing in the infrared spectrum, glowing like a beacon to anything with the right sensors. You emit roughly 100 watts of thermal radiation, a dim but perpetual broadcast of your presence. Light measures distance to the moon within millimeters. Lunar laser ranging experiments use retroreflectors left by Apollo astronauts and Soviet landers. Observatories fire laser pulses at these reflectors. About 1 photon in 10 quintillion returns to the telescope. By measuring the round-trip time, roughly 5 seconds, scientists calculate the moon's distance to within a few millimeters. This data revealed that the moon recedes from Earth by 3.8 centimeters per year due to tidal interactions. Light becomes a cosmic tape measure. Supernovae briefly outshine entire galaxies. A Type Ia supernova can reach an absolute magnitude of 19.3, radiating as much light as 5 billion suns. These explosions happen when a white dwarf accumulates matter from a companion star until it exceeds 1.4 solar masses, the Chandrasekhar limit, and collapses, triggering runaway fusion. The light curve is consistent across all Type Ia supernovae, making them standard candles for measuring cosmic distances. Saul Perlmutter, Brian Schmidt, and Adam Rees used Type Io supernovae to discover the universe's expansion is accelerating, earning the 2011 Nobel Prize. Light revealed dark energy. Mirrors reverse left and right, but not up and down. This puzzled people for centuries. The truth is, mirrors don't reverse anything. They reverse front and back. When you face a mirror, your actual right hand is on the mirror's left side from the mirror's perspective. The confusion comes from imagining yourself walking into the mirror. If you physically rotated to face the same direction as your reflection, you'd have to turn around your vertical axis, swapping left and right. A mirror simply reflects along the axis, perpendicular to its surface. Light knows no confusion. It just returns the way it came. Corner reflectors send light back exactly where it originated. 3 perpendicular mirrors arranged like the corner of a cube reflect light through 3 surfaces, reversing its direction precisely. This works regardless of the angle of incoming light. Bicycle reflectors and road signs use corner reflector designs. The retro reflectors on the moon are arrays of corner Q prisms. This is why laser ranging works. The light returns to almost exactly where it started, even across 400 kilometers. Light remembers its source. Chromatic aberration splits images into colored fringes. Simple lenses refract blue light more than red light, because refractive index varies with wavelength, a property called dispersion. This means different colors focus at slightly different distances. Early telescopes suffered from this. Isaac Newton believed it was unsolvable and invented the reflecting telescope in 1668 to avoid the problem. But in 1733, Chester Moore Hall discovered that combining crown glass and flint glass materials with different dispersion properties could cancel chromatic aberration. Achromatic doublets made refracting telescopes practical. Light taught lens makers to marry opposites. Thin film interference creates the colors on soap bubbles, oil slicks, and butterfly wings. When light reflects from the top and bottom surfaces of a thin, transparent layer, the two reflected waves interfere. Whether they reinforce or cancel depends on the film's thickness and the light's wavelength. A film 120 nanometers thick might cancel blue light and reinforce red. As the film's thickness changes, colors shift. Morpho butterflies have wing scales with layered structures creating brilliant blue through interference, not pigment. The blue remains vibrant even after centuries because it's structural. Light builds color from geometry. Scotopic vision uses only rods no color, in very dim light less than 0.01 lux. Your cone cells don't receive enough photons to activate. Only rods function in giving you vision, but no color perception. Everything appears shades of gray. Rods are about 100 times more sensitive than cones, but can't distinguish wavelengths. They peak at 498 nanometers blue-green light. This is called the Purkinje effect. After Jan Purkinje, who described it in 1825, red flowers appear dark in twilight, while blue flowers remain relatively bright. Your color vision shuts down, quietly unannounced. Light reveals itself only when abundant. Cats see better in darkness because of the tapetum lucidum. This reflective layer behind the retina bounces light back through photoreceptors, giving them a second chance to capture photons. It's why cat eyes glow in photographs. The camera flash reflects back. The tapetum improves light sensitivity by 40 to 50%, essential for nocturnal hunting. Humans lack this structure. Sharks, deer, and many nocturnal animals have it. The reflected light appears green, yellow, or blue depending on the animal. Light gets recycled through biology. Albedo measures how much light a surface reflects. Fresh snow reflects about 80 to 90% of incoming sunlight, high albedo. Ocean water reflects only about 6%, low albedo. Earth's average albedo is approximately 0.30, meaning 30% of sunlight reflects back to space. Climate scientists worry about declining albedo as polar ice melts. Darker ocean water absorbs more heat, accelerating warming in a feedback loop. Albedo also affects why you feel cooler wearing white shirts in summer. Light absorption determines temperature. Crepuscular rays, those shafts of light streaming through clouds, are parallel. They appear to diverge because of perspective, the same reason railroad tracks seem to converge at the horizon. The sun is so distant that its rays arrive essentially parallel. When clouds block some rays and allow others through, you see the beams. Dust and moisture scatter light, making the beams visible. The rays are called crepuscular, from crepusculum, Latin for twilight, because they're most dramatic at dawn and dusk when the sun is low. Light draws perspective lessons in the sky. Cherenkov radiation in nuclear reactor pools glows a haunting blue. Spent fuel rods emit beta particles, high-energy electrons that travel through water faster than light speed in water, which is 225,000 kilometers per second. These electrons create electromagnetic shock waves emitting photons concentrated in the blue and ultraviolet spectrum. The intensity relates to particle velocity. Pavel Cherenkov observed this in 1934 while studying radioactivity. Igor Tamm and Ilya Frank explained the mechanism in 1937. All three shared the 1958 Nobel Prize in Physics. Light emerges from motion exceeding its own local speed. Bremsstrahlung radiation, braking radiation in German, occurs when charged particles decelerate. When electrons slam into a metal target in an X-ray tube, they slow rapidly, converting kinetic energy to photons. The resulting X-rays have a continuous spectrum up to a maximum energy determined by the accelerating voltage. Wilhelm Röntgen discovered X-rays accidentally in 1895 while experimenting with cathode ray tubes. He noticed a fluorescent screen glowing across the room. He took the first X-ray image of his wife's hand, clearly showing bones and her wedding ring. She reportedly said, "I have seen my death." Light made the invisible skeleton visible. Synchrotron radiation happens when relativistic charged particles curve. Particle accelerators like the Large Hadron Collider constantly bend electrons and protons using magnetic fields. When particles moving near light speed change direction, they emit intense radiation tangent to their curved path. Synchrotron facilities exploit this, producing brilliant X-rays for research in materials, science, protein, crystallography, and chemistry. The European Synchrotron Radiation Facility in Grenoble generates X-rays 10 trillion times brighter than medical X-ray machines. Light becomes a research tool through forced turns. Your eye's blind spot exists where the optic nerve exits the retina. No photoreceptors cover that area, about 5 degrees temporal to your fovea. You don't notice it because your brain fills in the gap with information from surrounding areas and from the other eye. You can find your blind spot by closing your right eye, focusing on a point with your left eye, and moving a small object through your left visual field about 15 degrees to the left. The object vanishes briefly. Light leaves a hole in perception patched by neural invention. Diffraction limits resolution in optical systems. When light passes through a circular aperture like a camera lens, it doesn't create a perfect point. It produces an airy disk surrounded by dimmer rings. Two closely spaced points blur together if their airy disks overlap too much. The Rayleigh criterion states that 2 points are just resolvable when the central peak of one airy disk falls on the first minimum of the other. Angular resolution equals 1.22 LD, where L is wavelength and D is aperture diameter. This is why telescopes need large mirrors, not just to gather light, but to see fine detail. Hubble space. Telescope's 2.4-meter mirror achieves about 0.05 arcsecond resolution in visible light. Light imposes physical limits on clarity. Gravitational redshift happens when light climbs out of a gravity well. General relativity predicts that photons escaping strong gravitational fields lose energy, shifting toward longer wavelengths. In 1959, Robert Pound and Glenn Rebka verified this using gamma rays traveling up a 22.5-meter tower at Harvard. They measured a frequency shift of 2.5 parts in 1015, matching Einstein's prediction. Light from the sun shows a gravitational redshift of about 2 parts per million compared to laboratory sources. GPS satellites must account for gravitational blueshift clocks at altitude, experience weaker gravity, and run faster. Light bends to gravity's pull even without mass. The Doppler effect shifts light from moving objects. When a light source moves toward you, waves compress blueshift. Moving away, they stretch redshift. In 1848, Hippolyte Fizeau suggested this could measure stellar velocities. By 1868, William Huggins detected Doppler shifts in Sirius's spectrum. Edwin Hubble used redshift in 1929 to show distant galaxies recede from us, with velocity proportional to distance, Hubble's law. This revealed the universe's expansion. Police radar guns use microwave Doppler shift to measure car speeds. Medical ultrasound uses sound waves to measure blood flow. Light and its cousins across the electromagnetic spectrum track motion everywhere. Quasars emit light from supermassive black holes consuming matter. As gas spirals into a black hole, friction heats it to millions of degrees. The accretion disk glows brilliantly across the spectrum, X-rays ultraviolet visible light. Jets of particles accelerated by magnetic fields shoot out perpendicular to the disk at near light speed, emitting radio waves. Martin Schmidt identified the first quasar 3C 273 in 1963 by recognizing enormous redshift in its spectrum. It was 2 billion light-years away, yet appeared star-like. Quasars are the most luminous, persistent objects in the universe. A bright quasar can outshine its entire host galaxy of 100 billion stars. Light marks where matter falls into oblivion. Pulsars blink with extraordinary regularity. Jocelyn Bell Burnell discovered the first in 1967, a radio source pulsing every 1.337 seconds. Initially called LGM-1 for Little Green Men, it was soon recognized as a rotating neutron star. A pulsar is a stellar corpse collapsed core left after a supernova only about 20 kilometers wide, but containing 1.4 solar masses. It spins rapidly, often multiple times per second. A lighthouse beam of radiation sweeps space as it rotates. The millisecond pulsar PSR J1748-24468 rotates 716 times per second. Its equator moves at 24% of light speed. These stellar lighthouses keep time better than atomic clocks over short periods. Light becomes a cosmic metronome. Intensity follows the inverse square law. Double the distance from a point light source, and intensity drops to 1/4. Triple the distance 1/9. Photographers know this intuitively. Moving a flash twice as far makes the subject 4 times darker. The law emerges from geometry. Light spreads over the surface of an expanding sphere. Surface area equals 4πr2. As radius doubles, area quadruples, diluting the light. This applies to gravity sound radiation, any phenomenon spreading uniformly in 3 dimensions. Light teaches you that proximity matters profoundly. Iridescence in hummingbird feathers comes from microscopic structures. Barbules' tiny branches of feathers contain layers of air and melanin, creating interference effects. Different angles produce different colors. Unlike pigments that absorb specific wavelengths, structural color depends on viewing geometry. Turn a hummingbird, and its gorget shifts from brilliant red to black. Peacock feathers, beetle shells, and abalone nacre use the same principle. Evolution discovered nanophotonics millions of years before humans. Light becomes ornament through architecture. Your pupils constrict in bright light via the pupillary light reflex. Photoreceptors in your retina send signals through the optic nerve to the pretectal nucleus in the midbrain. This triggers the Edinger-Westphal nucleus, which activates the sphincter pupillae muscle via parasympathetic fibers. The entire reflex takes 200 to 300 milliseconds. Both pupils constrict together, even if only one eye receives light, called the consensual light reflex. Damage to this pathway helps neurologists diagnose injuries. Light tests the nervous system's integrity. Zodiacal dust particles are surprisingly large, 1 to 300 micrometers. Smaller dust would be blown out by radiation pressure. Larger particles would fall into the sun. Poynting-Robertson drag, the effect of absorbing and re-emitting sunlight, causes particles to slowly spiral inward. Dust survives only because asteroids and comets continually replenish the supply. About 40,000 tons of cosmic dust fall to Earth yearly, mostly as micrometeoroids. You've probably breathed ancient stardust. Light pressure sculpts the solar system's architecture. Sunlight reaching Earth delivers about 1/361 watts per square meter, the solar constant. This varies by about 3.5 watts due to solar cycles and Earth's elliptical orbit. Earth's orbit changes distance from the Sun by about 5 million kilometers over the year, closest in early January. Yet Northern Hemisphere summer occurs in July. This proves orbital distance matters less than axial tilt for seasons. The 23.5-degree tilt determines how directly sunlight strikes each hemisphere. Light explains why December is winter, despite proximity to the Sun. Ancient cultures track time by the stars. The heliacal rising of Sirius, when the star first became visible at dawn after a period of invisibility, signaled the annual flooding of the Nile around 3000 BC. Egyptians based their calendar on this event. Polynesians navigated thousands of kilometers across open ocean using star positions, wave patterns, and bird behavior. Navigators memorized the rising and setting positions of over 150 stars. They knew which stars hung directly over specific islands. Light from distant suns became a map written across the darkness. Stellar parallax proves Earth orbits the Sun. As Earth moves around its orbit nearby, stars appear to shift position relative to more distant stars. Friedrich Bessel first measured this in 1838 for the star 61 Cygni, a shift of 0.314 arcseconds, indicating a distance of about 11 light-years. The measurement required exquisite precision. An arcsecond is 3600th of a degree. Parallax gets smaller with distance. Stars farther than a few hundred light-years show parallax too tiny to measure from Earth's surface. The Gaia spacecraft launched in 2013 has measured positions and parallax for over 1.8 billion stars. Light's slight shift across 6 months reveals cosmic distances. Brown dwarfs glow, but never ignite true fusion. These failed stars have masses between 13 and 80 times Jupiter, not enough to sustain hydrogen fusion in their cores. They shine from leftover heat, from gravitational collapse, and from deuterium fusion, which requires lower temperatures. They gradually cool over billions of years, fading from red to infrared. The first confirmed brown dwarf, Gliese 229b, was discovered in 1995. They are surprisingly common. The Milky Way might contain 25 to 100 billion of them. Light whispers from objects that wanted to be stars but couldn't quite gather enough mass. Wolf-Rayet stars blaze so hot, their surfaces reach 200,000 Kelvin. These massive stars, over 25 solar masses, have blown away their hydrogen envelopes, exposing helium and carbon cores. Intense ultraviolet radiation drives stellar winds at speeds up to 2,000 kilometers per second. They lose mass rapidly, perhaps an entire solar mass every 10,000 years. Charles Wolf and Georges Rayet discovered this class in 1867 by analyzing their emission line spectra. Most Wolf-Rayet stars will explode as supernovae within a few million years. Light reveals stars dying spectacularly. The cosmic distance ladder uses multiple overlapping methods. Nearby stars get measured by parallax. Farther out, Cepheid variables stars whose brightness oscillates predictably based on their period act as standard candles. Henrietta Swan Leavitt discovered the period luminosity relationship in 1912 by studying Cepheids in the Small Magellanic Cloud. Beyond Cepheids type, IIA supernovae calibrate distances to billions of light years. At the farthest reaches, redshift becomes the primary tool. Each rung calibrates the next. Light builds a ladder to the edge of the observable universe. Neutron stars pack incredible density. A neutron star with 1.4 solar masses measures only about 20 kilometers across. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. Gravity at the surface is 200 billion times stronger than Earth's. Light escaping a neutron star experiences extreme gravitational redshift. Photons literally climb out of a gravity well, so deep it warps space-time severely. Despite containing more mass than the Sun, These stars shine faintly because their small surface area limits luminosity. The James Webb Space Telescope sees infrared light blocked by Earth's atmosphere. Launched in December 2021, JWST orbits the Sun at the L2 Lagrange point 1.5 million kilometers from Earth. Its 6.5-meter gold-coated beryllium mirror collects light from the universe's first galaxies, formed just 200 million years after the Big Bang. High redshifts stretch their visible light into infrared. JWST operates at 40 Kelvin, colder than Pluto, to prevent its own heat from overwhelming faint signals. The telescope sees through dust clouds where stars are born. Light from the infant universe reaches us finally, 13.6 billion years delayed. Very Long Baseline Interferometry combines radio telescopes across continents. By recording signals with atomic clock precision and later correlating data, astronomers create a virtual telescope as large as Earth itself. Resolution depends on baseline distance, not individual telescope size. The Event Horizon Telescope Network achieved 20 microsecond resolution to image black hole M87's shadow. Radio interferometry revealed the structure of quasars mapped jets from black holes and track spacecraft. Light at radio wavelengths teaches precision through separation. Quantum dots are nanoscale semiconductors that glow specific colors based on size. A quantum dot 2 nanometers wide emits blue light. Make it 6 nanometers and it emits red. The reason lies in quantum confinement. Electrons trapped in tiny spaces have discrete energy levels. As the dot gets smaller, energy gaps widen, shifting emission toward blue. Alexei Ekimov discovered quantum dots in glass in 1981. Maunji Bawendi developed methods to synthesize high-quality dots in 1993. Modern TVs use quantum dots for vivid colors. Medicine uses them to tag and track specific cells. Light from artificial atoms tuned by geometry. Airglow makes Earth's atmosphere luminous even at night. Photochemical reactions in the upper atmosphere, especially around 90 to 100 kilometers altitude, produce faint emissions. Oxygen atoms recombining into O2 emit green light at 557.7 nanometers. Sodium atoms from meteors glow yellow. Hydroxyl radicals glow in near-infrared. The air glow is about 1 million times fainter than daylight, but detectable from space. Astronauts photograph it as a thin, glowing shell around Earth's limb. The atmosphere shines quietly without stars or sun. Lasers can trap and manipulate individual atoms. Optical lattices use intersecting laser beams to create standing wave patterns, bright regions, and dark nodes arranged in three-dimensional grids. Atoms collect in the light intensity peaks or nodes, depending on their properties. Researchers adjust laser wavelengths and intensities to move atoms, creating artificial crystals of cold atoms. These quantum simulators model solid-state physics test, many-body quantum theories, and might someday enable quantum computers. Light became scaffolding for matter arranged by wavelength. Laser guide stars create artificial reference points for adaptive optics. Telescopes on Earth suffer atmospheric turbulence that blurs images. Adaptive optic systems measure this distortion using a bright star near the science target and adjust a deformable mirror hundreds of times per second to compensate. But most fields lack a bright natural star. Solution: create one. A powerful sodium laser tuned to 589 nanometers excites sodium atoms in the mesosphere at 90 kilometers altitude. These atoms glow, producing an artificial star wherever astronomers need it. The Keck Observatory in Hawaii uses this technique routinely. Light invents its own calibration. Solar sails propel spacecraft using photon pressure. Each photon hitting a reflective surface transfers momentum equal to 2p for perfect reflection, where p is the photon's momentum. Sunlight at Earth's distance provides about 9 micronewtons of force per square meter. Japan's Ikaro spacecraft, launched in 2010, deployed a 200 square meter sail and successfully demonstrated solar sailing to Venus. The LightSail 2, launched in 2019, raised its orbit using only sunlight. Future missions might use ground-based lasers to push sails to a significant fraction of light speed, potentially reaching Alpha Centauri in decades rather than millennia. Light becomes propulsion without propellant. X-ray crystallography reveals atomic structure using light's shorter cousin. When X-rays wavelengths around 0.1 nanometers strike a crystal, they diffract according to the arrangement of atoms. The resulting pattern of spots encodes the crystal structure. Max von Laue discovered X-ray diffraction in 1912. William Lawrence Bragg developed Bragg's law relating diffraction angles to atomic spacing and solved the first structures at age 22. Rosalind Franklin's X-ray images of DNA, Photo 51, taken in 1952, revealed the double helix. Dorothy Hodgkin mapped penicillin vitamin B12 and insulin structures, winning the 1964 Nobel Prize. Light made the invisible alphabet of matter readable. Gamma-ray bursts are the universe's brightest explosions. For a few seconds, a gamma-ray burst can outshine all the stars in the observable universe combined. They occur about once per day, randomly distributed across the sky. The longest bursts, lasting tens of seconds, come from collapsing massive stars. Short bursts under 2 seconds come from merging neutron stars. The burst detected in October 2022, labeled the BOAT, brightest of all time saturated detectors across the solar system. It originated 2.4 billion light-years away, yet was bright enough to affect Earth's ionosphere. Light arrives from catastrophes unimaginable in violence. Phosphorescence glows long after illumination stops. Unlike fluorescence, which emits light only during excitation, phosphorescent materials trap excited electrons in metastable states. These electrons slowly return to ground states, emitting photons over seconds, minutes, or hours. Zinc sulfide doped with copper glows green for hours. A strontium illuminate doped with europium glows even longer. The glow-in-the-dark stars on children's ceilings use this chemistry. You can recharge them with light like a battery. Light stores itself in atoms for delayed release. Your retina consumes more oxygen per gram than any other tissue in your body. Photoreceptors constantly regenerate visual pigments, maintain ion gradients, and process signals. This demands enormous energy. The choroid layer behind the retina supplies oxygen-rich blood at high flow rates. If blood supply is interrupted for even minutes, photoreceptors die. Retinal detachment is a medical emergency for this reason. Your ability to see light requires infrastructure comparable to high-performance computing. Vision is metabolically expensive. Superluminous supernovae shine 10 to 100 times brighter than ordinary supernovae. Discovered in the 2000s, their energy source puzzled astronomers. Radioactive decay of nickel-56 can't explain the luminosity. Current theories suggest magnetar formation, newborn neutron stars spinning hundreds of times per second with magnetic fields trillions of times Earth's strength. Rotational energy converts to light. Or perhaps superluminous supernovae result from pair instability collapse in stars over 130 solar masses. Physics not possible in smaller stars. These rare events appear in distant galaxies. Light signals, physics at extremes we can't replicate. Thin film coatings on lenses reduce reflections. Uncoated glass reflects about 4% of light at each surface. A lens with multiple elements can lose significant light to reflections. Anti-reflective coatings use quarter-wavelength thick layers of materials with intermediate refractive indices. Magnesium fluoride with an index around 1.38 works well on glass with index 1.52. Light reflected from the coating's top surface interferes destructively with light reflected from the glass beneath. modern multi-layer coatings reduce reflection to under 0.1%. Camera lenses appear purple or green, the colors not suppressed by the coating design. Light gets canceled by light through precise layering. The electromagnetic spectrum spans over 15 orders of magnitude and wavelength. Radio waves stretch to meters or kilometers. Microwaves measure centimeters. Infrared covers micrometers. Visible light occupies 400 to 700 nanometers, less than 1 octave. Ultraviolet X-rays and gamma rays shrink to atomic and nuclear scales. All are the same phenomenon, electromagnetic waves differing only in wavelength and energy. Your eyes evolved to sense the narrow band where the sun emits most strongly, and Earth's atmosphere is transparent. Light shows you one thin slice of a vast spectrum. Redshift measures how fast galaxies recede. The most distant galaxies have redshifts above 10, meaning light stretched by a factor of 11. Wavelengths that left as ultraviolet arrive as infrared. These galaxies existed when the universe was less than 500 million years old. We see them not as they are, but as they were. The photons have traveled over 13 billion years. During their journey, space itself expanded, carrying galaxies apart and stretching the light. Distance and look-back time become inseparable. Light travels through expanding space, arriving older than the universe it left. Your eyes produce their own light through biophotons. Living tissues emit ultra-weak photons, about 10 to several hundred per second, per square centimeter of skin, for metabolic reactions. Eyes produce particularly intense biophoton emission, detectable by sensitive photomultipliers. The biological function, if any, remains unknown. Possibly it's just byproduct of chemistry, or perhaps cells communicate using photons. Either way, you literally glow faintly in the visible spectrum, independent of body heat. Light escapes from the chemistry of being alive. Leaves appear green because chlorophyll reflects green light while absorbing red and blue. Chlorophyll A absorbs strongly around 430 nanometers blue and 662 nanometers red. The green wavelengths around 550 nanometers bounce back unused. This seems wasteful. Why reject green light when the sun emits it most strongly? One theory suggests early photosynthetic organisms used retinol-based pigments that absorbed green, forcing later chlorophyll-based life to use what remained. Another proposes that rejecting green prevents oversaturation damage in bright light. Evolution chose inefficiency for resilience. Light shaped the color of life. Autumn colors were always there hidden. Chlorophyll dominates during summer, masking carotenoids, yellow and orange pigments that are present all along. As days shorten and temperatures drop, trees stop producing chlorophyll. The green fades, revealing the yellows and oranges underneath. Red and purple anthocyanins are synthesized fresh in autumn, possibly protecting leaves during nutrient recovery. Peak fall color depends on weather. Sunny days and cool nights produce the most anthocyanins. Sugar maples turn brilliant red. Aspens turn gold. Oaks turn brown from tannins. Light and chemistry paint forests through seasonal withdrawal. Bioluminescent fungi glow green at night. Species like Pinellus stypticus and Omphalodus olearius emit light around 520 to 530 nanometers through luciferin-luciferase reactions similar to fireflies. The ecological function remains debated. Research published in 2015 suggests the glow attracts insects which disperse spores. The fungi glow most intensely at night when beetles and flies are active. Around 80 species worldwide exhibit bioluminescence. In Brazilian forests, Neonothopanus gardneri glows bright enough to read by. Light becomes a reproductive strategy for organisms that never move. The sun loses 4 million tons of mass every second through fusion. Einstein's E=mc² MC2 predicts this mass energy conversion. Hydrogen fusing into helium releases 0.7% of the mass as energy. That energy eventually escapes as light. Over the sun's 4.6 billion year lifetime, it has converted roughly 100 Earth masses into radiant energy. At this rate, the sun will exhaust hydrogen in its core in about 5 billion years. Light slowly consumes its source. Solar flares release as much energy as 10 million volcanic eruptions. Magnetic field lines in the sun's corona twist and suddenly reconnect, converting magnetic energy to kinetic and thermal energy. Particles accelerate to near light speed. X-rays and extreme ultraviolet radiation flood space within minutes. The largest flare recorded in 2003 saturated sensors at X28 class, probably higher. The Carrington event of 1859 caused auroras visible near the equator and telegraphs to spark. A similar flare today would damage satellites and power grids. Light from the sun arrives both as steady glow and sudden violence. Stars twinkle, but planets don't. Stars appear as point sources effectively zero size from Earth. Atmospheric turbulence shifts the star's apparent position, randomly making it shimmer. Planets show small disks, perhaps 1 arc-second wide. The disk averages out turbulence fluctuations. Ancient astronomers noticed planets stayed steady while stars flickered. The word planet comes from Greek planets wanderer. They moved against the fixed stars and behaved differently. Light distinguished categories before telescopes existed. Dark adapted vision takes 30 to 45 minutes to fully develop. After about 10 minutes in darkness, cone-based vision completes adaptation. But rod cells continue increasing sensitivity for another 20 to 35 minutes, reaching maximum sensitivity around 100,000 times greater than in bright light. This adaptation involves rhodopsin regeneration and neural adjustments. Astronomers use red flashlights because red light around 650 nanometers barely activates rhodopsin, which peaks at 498 nanometers. You can preserve night vision while reading star charts. Light respects wavelength boundaries. The Hubble Deep Field image exposed a tiny patch of sky for 10 days. The region near the Big Dipper appeared empty to ground telescopes, no bright stars or galaxies. In December 1995, Hubble stared at this blank area totaling 342 exposures. The resulting image revealed about 3,000 galaxies in a region the size of a grain of sand held at arm's length. Almost every object in the image is a galaxy containing billions of stars. The 2003 Hubble Ultra Deep Field went deeper, collecting photons for 11.3 days, finding 10,000 galaxies, some formed just 400 to 800 million years after the Big Bang. Light accumulates to reveal infinity in emptiness. Gravitational microlensing detects exoplanets. When a star passes in front of a more distant star from Earth's perspective, gravity bends the background star's light, briefly brightening it. If the foreground star has a planet, the planet's gravity creates a secondary spike in brightness lasting hours to days. The method finds planets at distances where other techniques fail out, to 25,000 light-years. In 2006, the Ogill project detected a 5.5 Earth-mass planet this way. Light bends to mass, revealing worlds too dim to see directly. Olbers's paradox asks why the night sky is dark. If the universe is infinite and eternal, with stars uniformly distributed, every line of sight should end at a star's surface. The sky should glow as bright as the sun everywhere. Heinrich Olbers stated this paradox in 1823, though earlier thinkers noted it. The resolution the universe is not infinite in age. Light from distant stars hasn't had time to reach us yet. Also, cosmic expansion redshifts distant light out of the visible spectrum. The darkness between stars proves the universe had a beginning. Darkness becomes evidence of cosmic youth. Light pollution disrupts ecosystems. Artificial lights confuse migratory birds, causing collisions with buildings. Sea turtle hatchlings navigate toward moonlight, reflecting off ocean waves, but coastal lights mislead them inland where they die. Nocturnal insects spiral into lights until exhaustion. Plants near streetlights delay autumn leaf drop, risking frost damage. Humans exposed to light at night suppress melatonin, disrupting sleep and increasing health risks. The Milky Way is invisible to 1/3 of humanity, including 60% of Europeans and 80% of Americans. Light improperly used erases the night. Rayleigh scattering makes the sky blue. Air molecules, mostly nitrogen and oxygen, are smaller than visible light wavelengths. When sunlight hits these molecules, shorter wavelengths scatter more efficiently. Blue light, 475 nm, scatters about 10 times more than red light's 650 nm. The entire sky becomes a scattered blue source. Lord Rayleigh derived the mathematics in 1871, showing scattering intensity is inversely proportional to the fourth power of wavelength. This is why sunsets appear red at low sun angles. Light travels through more atmosphere, scattering away blues and greens, leaving reds and oranges. Light color codes the time of day through atmosphere thickness. Sodium vapor lamps glow orange-yellow. These streetlights contain sodium vapor that emits nearly monochromatic light at 589 nanometers, the sodium D-line doublet. Under sodium lights, most colors appear gray or brown because the narrow spectrum doesn't activate red or blue cone cells. High-pressure sodium lamps, introduced in the 1960s, produce broader spectra with better color rendering. Low-pressure sodium lamps, though nearly 200 lumens per watt, the most efficient light source before LEDs, rendered colors so poorly they fell out of favor. Astronomers loved them because the narrow spectrum could be filtered out at observatories. Light sacrificed color for efficiency. Stained glass achieves colors through metallic oxides. Cobalt oxide produces deep blue. Copper oxide creates green or red, depending on oxidation state. Gold chloride makes ruby red, the famous cranberry glass. Medieval artisans didn't understand chemistry, but knew recipes by trial. Chartres Cathedral, built 1194 to 1220, contains windows with Chartres blue, an intensely vivid cobalt blue that may have involved specific impurities or techniques now lost. Light transmitted through stained glass creates luminous color, impossible with reflected light. The windows glow from within when sunlit. Light transformed worship spaces into jewel boxes. Calcite crystals show double refraction. When light enters calcite calcium carbonate, it splits into two rays traveling at different speeds along different paths, both obeying Snell's law but with different refractive indices. This birefringence creates double images. Place calcite over text and you see two sets of letters offset from each other. Vikings may have used sunstones, possibly calcite, to navigate on cloudy days by detecting polarized skylight. Calcite can determine the sun's position even when it's hidden. Light reveals itself through the physics of crystal structure. The Foucault pendulum uses Earth's rotation to twist light paths. Well, not directly, but Léon Foucault invented the pendulum in 1851 to demonstrate Earth's rotation. He also measured the speed of light in 1862 using rotating mirrors, improving on Fizeau's method. His measurement of 298,000 kilometers per second was remarkably accurate. Foucault proved light travels slower in water than in air, confirming the wave theory over Newton's corpuscular theory. His experiments demonstrated that light could be tamed with precise mechanics and clever geometry. Light submitted to measurement through human ingenuity. Lasers can create holograms that store thousands of images in the same space. Volume holograms record interference patterns throughout a photosensitive material's thickness, not just on its surface. By changing the angle or wavelength of illuminating light, different images appear. Holographic storage might pack terabytes in a sugar cube volume. The technology exists but hasn't displaced magnetic or solid-state storage commercially. Still, credit cards and currency use holograms as security features. Light layers information in 3 dimensions. Light carries angular momentum. circularly polarized light can spin objects. In 1936, Richard Bethe measured torque on a birefringent plate suspended by a thin fiber when illuminated with polarized light. The plate rotated as it converted photon angular momentum to mechanical rotation. Lasers with orbital angular momentum, where the beam has a helical wavefront, can transfer even more. Researchers use optical torque to spin microscopic particles at millions of revolutions per minute. Light doesn't just push, it twists. Supernovae create most elements heavier than iron. Fusion inside stars produces elements up to iron, but fusing iron requires energy input. During a supernova's collapse, temperatures and pressures become extreme enough for rapid neutron capture the R process. Neutrons bombard heavy nuclei building elements like gold, platinum, and uranium within seconds. The explosion scatters these elements across space. Every gold atom in existence was likely forged in a supernova or neutron-star collision. The light you see from a supernova announces the birth of heavy elements now drifting through galaxies. Your gold jewelry contains stardust from ancient stellar deaths. X-ray binaries shine by cannibalism. A compact object neutron star, or black hole, orbits a normal star close enough to strip matter away. Gas spirals into an accretion disk around the compact object, heating to millions of degrees and emitting X-rays. Cygnus X1, discovered in 1964, was the first strong black hole candidate. Matter falling in radiates up to 10% of its mass energy, far more efficient than fusion's 0.7%. The X-rays flicker on millisecond time scales as blobs of matter orbit near the event horizon. Light marks where stars consume each other. The Planck length, about 1.6 Scal 10 to 35 meters, represents the scale where quantum gravity becomes important. At this size, space-time itself might be grainy rather than smooth. Photons with wavelengths near the Planck length would have energies around 1019 GeV, far beyond any particle accelerator. These Planck-scale photons likely existed in the first 1043 seconds after the Big Bang. Current physics cannot describe them precisely. General relativity and quantum mechanics conflict at these extremes. Light at the smallest scales becomes a question mark, pointing toward theories we haven't yet discovered. Opals diffract light through nanoscale spheres. Precious opal contains uniform silica spheres, about 150 to 300 nanometers in diameter, packed in regular arrays. Light waves diffract off these structures, with different wavelengths reinforcing at different angles. Rotate an opal, and colors shift red, green, blue, swirling across the surface. The structure resembles colloidal crystals. Synthetic opals created in the 1970s use similar sphere arrays. Nature assembled nanophotonics over millions of years as silica precipitated slowly underground. Light plays in organized chaos. Cosmic rays are not rays, they're particles. But when they hit Earth's atmosphere at near light speed, they create cascades of secondary particles and Cherenkov radiation. Victor Hess discovered cosmic rays in 1912 by taking electroscopes up in balloons and detecting increased ionization with altitude. The highest energy cosmic ray ever detected, the Oh My God particle in 1991, carried 3 1020 electron volts. The kinetic energy of a baseball traveling 60 mFur concentrated in a single proton. Its source remains unknown. Light's cousins arrive from beyond the galaxy carrying mysteries. Shadows on the moon are absolute black. Without atmosphere to scatter light, shadowed areas receive no illumination except from reflected Earthlight or distant stars. Apollo astronauts reported stepping from brilliant sunlight into pitch darkness within a single stride. Cameras couldn't capture details in both sunlit and shadowed areas. Simultaneously, the contrast exceeded film latitude by orders of magnitude. Buzz Aldrin described the boundary as a peculiar, menacing transition. Light divides the lunar surface into extremes with no gentle gradient between. Earth shines on the moon. Earthlight is about 50 times brighter than moonlight on Earth because Earth has higher albedo and presents a larger disk. During a lunar night, 14 Earth days long, Earthlight provides enough illumination for astronauts to navigate without artificial lights. Leonardo da Vinci correctly explained the old moon in the new moon's arms. In 1510, the faint glow on the unlit portion of a crescent moon comes from sunlight reflecting off Earth. Light bounces between worlds. The Eiffel Tower changes height by 15 centimeters between summer and winter. Iron expands when heated. The sun warms the metal, causing thermal expansion. Engineers calculated this during design in the 1880s. Light delivers energy that physically reshapes structures. On a smaller scale, sunlight causes sidewalks to crack and rails to buckle during heat waves. Light carries consequences in the form of heat. Infrared thermography reveals heat invisible to eyes. Every object above absolute zero emits thermal radiation. Warmer objects emit more intensely and at shorter wavelengths. Infrared cameras detect wavelengths from about 3 to 14 micrometers, translating temperature into visible images. Firefighters use thermal cameras to see through smoke. Building inspectors find heat leaks. Medical thermography identifies inflammation. Military night vision relies on thermal imaging. William Herschel discovered infrared radiation in 1800 by placing a thermometer beyond red in a prism spectrum and noting temperature rise. Light extends beyond human vision into heat. The ozone layer absorbs UVC and most UVB radiation. Ozone molecules, 3 oxygen atoms bound together, form in the stratosphere when UV light splits O2 molecules. Free oxygen atoms then combine with other O2 molecules to create O3. This ozone absorbs UV between 200 and 315 nanometers, preventing it from reaching Earth's surface. Without this shield complex, life would struggle to exist on land. Chlorofluorocarbons released from 1930s to 1990s destroyed ozone, creating the Antarctic ozone hole. The 1987 Montreal Protocol banned CFCs. The ozone layer is slowly recovering, full recovery expected around 2070. Light-shaped atmospheric chemistry that protects biology. Desert mirages can appear as lakes. Hot ground heats the air directly above it, creating a temperature gradient. Light from the sky traveling downward at a shallow angle bends, refracts through layers of air with different densities. At some point, the refraction becomes total internal reflection. The light curves back upward without reaching the ground. Your brain interprets this as a reflection from water. Occasionally, you'll see cars or trees inverted, appearing to float above the horizon. The physics is identical to mirages on hot roads. Light constructs illusions from temperature. Smartphone screens use liquid crystals. Thin film transistors control electric fields at each pixel. These fields rotate liquid crystal molecules, which change how much light passes through polarizing filters. Backlight provides illumination. LEDs emit white light, or earlier cold cathode fluorescent tubes. Color filters, red, green, blue subpixels create the image. LCD technology evolved from research in the 1960s by RCA and others. James Ferguson developed practical twisted pneumatic displays in 1969. Billions of people carry these light manipulation devices. Light becomes information through molecular alignment. Fluorescent minerals glow under UV light. Calcite fluoresces red or orange. Willemite glows green. Fluorite, the namesake of fluorescence, glows blue. George Stokes studied this phenomenon in the 1850s, noting that fluorite absorbed invisible UV and emitted visible blue light. The term fluorescence comes from fluorite. Museums display fluorescent mineral exhibits under UV lamps. Rocks that look ordinary in daylight burst into vivid color. Some scorpions fluoresce blue-green under UV, allowing nighttime detection. Light unlocks hidden colors through energy conversion. Fiber optics revolutionized telecommunications. A single optical fiber can carry over 100 terabits per second using wavelength division, multiplexing, sending multiple wavelengths simultaneously through the same fiber. Data travels as pulses of infrared light around 1,550 nanometers, where silica glass has minimal attenuation. Erbium-doped fiber amplifiers boost signals over long distances without electrical conversion. The first transatlantic fiber optic cable, TAT-8, began operation in 1988 with 280 megabits per second capacity, 3 lines in modern terms. Today's cables carry thousands of times more. The internet runs on light. Chromatic dispersion limits fiber optic bandwidth. Different wavelengths travel at slightly different speeds through glass. A short pulse containing multiple wavelengths spreads out over distance. At 310 nanometers, the zero dispersion wavelength for standard single-mode fiber, this effect minimizes. Engineers use dispersion-shifted fibers or compensating fibers to manage this. At 1,550 nanometers, erbium amplifiers work best, but dispersion increases. The solution involves dispersion compensation modules that introduce opposite dispersion. Light pulses must be carefully shaped to maintain high data rates over thousands of kilometers. Sunspots are cooler than surrounding photosphere. They appear dark around 3,800 Kelvin compared to 5,800 Kelvin for the rest of the solar surface. Strong magnetic fields about 2,500 Gauss inhibit convection, preventing hot plasma from rising. Despite being cool, sunspots still glow brightly. If you could see one in isolation against black space, it would appear brilliant orange. They seem dark only by contrast. Galileo observed sunspots with telescopes in 1612, challenging the belief that the sun was perfect and unchanging. Light revealed imperfection in celestial spheres. Sunspot cycles average 11 years. The number of sunspots rises and falls roughly in this period, though cycles vary from 9 to 14 years. At solar maximum, dozens of sunspot groups appear. At solar minimum, days or weeks pass without any. The sun's magnetic field reverses each cycle, so the full magnetic cycle takes about 22 years. Astronomer Heinrich Schwabe discovered the cycle in 1843 after 17 years of patient observation. Solar cycles affect Earth's climate slightly, about 0.1% variation in solar irradiance, and influence auroras, radio communications, and satellite operations. Light from the sun fluctuates with magnetic rhythms. Corona visible during total solar eclipses reaches millions of degrees. The sun's surface is 5,800 K, but the corona, the outer atmosphere, exceeds 1 million K. This violates intuition temperature, increasing with distance from the heat source. The heating mechanism involves magnetic fields and plasma waves, though details remain debated. The corona's low density means you can't feel its heat directly. It emits strongly in X-rays and extreme UV invisible to human eyes. During eclipses, the corona appears as a pearly white halo with streamers. Light reveals the sun's atmosphere only when the bright photosphere is hidden. Laser interferometer gravitational wave detectors measure distance changes smaller than a proton's width. LIGO's arms stretch 4 kilometers. Gravitational waves alter this length by about 10 to 18 meters, a thousandth the diameter of a proton. The detector splits a laser beam, sends each part down, perpendicular arms, reflects off mirrors, and recombines the beams. Normally, they interfere destructively. A gravitational wave shifts the interference pattern, creating a brief signal. Rainer Weiss proposed the technique in 1972. The first detection occurred September 14, 2015, gravitational waves from merging black holes 1.3 billion light-years away. Weiss, Kip Thorne, and Barry Barish won the 2017 Nobel Prize. Light became a ruler for space-time itself. Fast radio bursts last milliseconds, but outshine entire galaxies. First detected in 2007 by Duncan Lorimer using archived pulsar survey data, These intense radio pulses originate from the distant galaxies. The Lorimer burst came from about 3 billion light-years away. Over 800 FRBs have been detected since. Most occur once and never repeat. A few repeat irregularly. The source remains uncertain, possibly magnet or flares, colliding neutron stars, or something entirely novel. The bursts show dispersion consistent with traveling through ionized gas across cosmic distances. Light's radio wavelengths arrive carrying unsolved mysteries. The cosmic neutrino background fills space. About 1 second after the Big Bang, the universe cooled enough for neutrinos to decouple from matter. These primordial neutrinos, about 336 per cubic centimeter, still exist, redshifted by expansion to energies around 0.0 electron volts. They have never been detected directly because they interact so weakly. The cosmic microwave background represents photons from 380,000 years after the Big Bang. The neutrino background is older from when the universe was 1 second old. Light has an older sibling particle that touches almost nothing. Gamma-ray astronomy requires space telescopes. Earth's atmosphere absorbs gamma rays completely fortunate for life. The Compton Gamma Ray Observatory operational 1991-2000 detected thousands of gamma ray sources. The Fermi Gamma Ray Space Telescope launched 2008 maps the gamma ray sky continuously. Gamma rays reveal neutron stars, supernova remnants, active galactic nuclei, and gamma ray bursts. Some blazars galaxies with jets pointed toward Earth shine more brightly in gamma rays than any other wavelength. Light at the highest energies requires viewing from space. Photons can entangle with atoms. In 2012, researchers entangled a photon with an ytterbium ion, then separated them by 1 meter. Measuring the photon's polarization instantly determined the ion's quantum state. This enables quantum networks where photons carry information between atom-based quantum processors. Entanglement doesn't transmit information faster than light. You need classical communication to interpret results, but it allows correlations impossible in classical physics. Light and matter became quantum partners. Magneto-optical traps capture atoms using light. 6 laser beams arranged in 3 perpendicular pairs bathe a region in light tuned, slightly below an atomic transition frequency. Atoms moving toward a beam see it. Doppler shifted into resonance absorb photons and slow down optical molasses. Adding a magnetic field makes the trap tighter. Atoms collect at the magnetic field's center, cooled to microkelvin temperatures. Researchers use magneto-optical traps to study quantum gases, atomic clocks, and quantum simulation. Light builds cages from photon momentum. The sun's core produces neutrinos from fusion. About 65 billion solar neutrinos pass through each square centimeter of your body every second. They almost never interact. A neutrino could pass through a light year of lead with only 50% chance of absorption. Raymond Davis Jr. built a detector, a tank of cleaning fluid deep in a South Dakota mine, and in the 1960s detected only 1/3 the predicted neutrinos. This solar neutrino problem lasted decades. The solution neutrinos oscillate between 3 types during their journey. Davis detected only 1 type. His experiment confirmed the sun's core reaches 15 million Kelvin hot enough for fusion. He shared the 2002 Nobel Prize. Light's neutral cousins confirmed stellar physics. Blue light is more hazardous to your retina than red light. Photons carry energy inversely proportional to wavelength. Blue photons at 400 nanometers carry nearly twice the energy of red photons at 700 nanometers. High-energy photons can damage photoreceptors and retinal pigment epithelium over time. Excessive blue light exposure might contribute to age-related macular degeneration, though evidence is still accumulating. The lens yellows with age blocking more blue light and protecting the retina and natural filter. Light at shorter wavelengths comes with costs. Ancient starlight contains information about early galaxies. The James Webb Space Telescope detected galaxies at redshift 13 existing just 300 million years after the Big Bang. Their light has traveled for 13.4 billion years. We see these galaxies not as they are, they've long since evolved or merged, but as they were when the universe was 2% of its current age. Some are surprisingly bright and massive, challenging models of galaxy formation. Each photon is a time capsule. Light brings history without editorials. Brightness of stars as seen from Earth follows the magnitude scale. Hipparchus created this system around 129 BC, ranking visible stars from magnitude 1 brightest to 6 faintest. In 1856, Norman Pogson formalized it logarithmically. A difference of 5 magnitudes equals a factor of 100 in brightness. Each magnitude is roughly 2.512 times brighter than the next. Sirius shines at magnitude 1.46. Venus reaches 4.6. The full moon is 12.6. The sun is 26.7. The faintest objects Hubble detects reach magnitude 31, about 4 billion times fainter than human eyes can see. Light span scales beyond intuition. Moonlight is actually sunlight reflected. The moon's surface reflects only about 12% of light that hits at lower albedo than fresh asphalt. Its heavily cratered regolith scatters light poorly. Yet, even this dim reflection provides enough illumination to cast shadows on Earth. Full moonlight measures about 0.25 lux compared to sunlight's 100,000 lux, roughly 400,000 times dimmer. Your eyes adapt, switching from cone-dominated photopic vision to raw-dominated scotopic vision. Colors fade. The world turns to silver and shadow. Light borrowed from the sun paints nights in monochrome. The moon's phases follow a 29.5-day cycle. This synodic month differs from the sidereal month 27.3 days because Earth moves along its orbit. The moon must travel slightly more than 360 degrees to return to the same phase relative to the sun. Ancient calendars worldwide use lunar months. The word month derives from moon. Islamic calendars remain purely lunar, causing holidays to drift through seasons. Hebrew and Chinese calendars use lunisolar systems, adding leap months periodically. Light's rhythm from the moon organized human time for millennia. Solar eclipses happen only during new moon. The moon must pass between Earth and the sun, but the moon's orbit tilts 5.1 degrees relative to Earth's orbital plane, the ecliptic. Most new moons pass above or below the sun from Earth's perspective. Eclipses occur only when new moon coincides with the moon crossing the ecliptic plane. 2 to 5 solar eclipses happen annually somewhere on Earth. Total solar eclipses are rare at any given location, averaging once every 375 years. The shadow path crosses Earth at speeds over 1,700 kilometers per hour. Light's brief denial creates spectacle. Lunar eclipses turn the moon red. Earth's shadow has 2 parts: the umbra, complete shadow, and penumbra, partial shadow. During a total lunar eclipse, the moon enters Earth's umbra, but Earth's atmosphere refracts sunlight around the planet's edges, bending red wavelengths into the shadow. Blue light scatters away the same Rayleigh scattering that makes the sky blue. The moon glows deep red, illuminated by all Earth's sunrises and sunsets simultaneously projected onto it. Eclipse duration can reach 107 minutes, the time for the moon to cross Earth's umbral shadow. Light finds a way even through planet-sized obstacles. Light sails could reach Alpha Centauri in decades. The Breakthrough Starshot initiative, proposed in 2016, envisions Gram-scale spacecraft with meter-wide reflective sails. Ground-based laser arrays, 100 gigawatts total power, would push these craft to 20% of light speed. At that velocity, they'd reach Alpha Centauri in about 20 years. The challenge is immense. Lasers must focus on tiny sails across millions of kilometers, survive interstellar dust impacts, and transmit data back across 4.37 light-years. But light makes interstellar travel conceivable within human lifetimes. Photons become starship fuel. Cherenkov radiation detectors catch neutrinos. The Super Kamiokande detector in Japan holds 50,000 tons of ultra-pure water surrounded by 11,000 photomultiplier tubes. When a neutrino rarely interacts with water, it produces charged particles that travel faster than light speed in water. These particles emit Cherenkov radiation, a cone of blue light. Photomultipliers detect the light reconstructing the neutrino's direction and energy. In 1987, Super Kamiokande's predecessor, Kamiokandes 2, detected neutrinos from supernova 1987A in the Large Magellanic Cloud, 168,000 light-years away. 11 neutrinos arrived within 13 seconds. Light's cousins confirm stellar collapse theory. Photographic film chemistry captures light permanently. Silver halide crystals, silver bromide chloride, or iodide embedded in gelatin coat the film. Photons striking a crystal provide energy to free silver ions, which combine with electrons to form metallic silver atoms. These create a latent image in visible clusters of silver atoms. Developer chemicals reduce additional silver ions at these nucleation sites, amplifying the image. Fixer removes unexposed silver halides. The result? A negative where exposed areas appear dark with metallic silver. Color film uses 3 emulsion layers sensitive to red, green, and blue light, with color couplers, creating dyes during development. Light leaves its trace through chemistry spanning the periodic table. Daguerreotypes were the first practical photographs. Louis Daguerre announced the process in 1839. A silver-plated copper sheet was polished treated with iodine vapor to create light-sensitive silver iodide exposed in a camera for minutes to hours, then developed over heated mercury. Mercury vapor formed an amalgam with exposed silver, creating the image. Daguerreotypes showed extraordinary detail, but were one of a kind. No negative existed to make copies. Early portraits required subjects to remain motionless for 30 seconds or longer. Head braces kept people steady. Nobody smiled, holding a smile that long is uncomfortable. Light demanded stillness to be captured. Photons can be delayed in optical fiber. Researchers have stored light pulses for over a minute by converting photons into atomic excitations in rubidium vapor, holding the quantum state, then converting it back to light. This quantum memory might enable quantum repeaters for long-distance quantum communication. In ordinary fiber light takes about 5 milliseconds to travel 1,000 kilometers impossibly fast for some applications. Slow light techniques reduce group velocity to meters per second by making materials extremely dispersive. Light can be taught to wait. Gravitational lensing reveals dark matter. Galaxy clusters contain far more mass than visible stars and gas account for. We know this because their gravitational lensing effects bending background galaxy light require enormous mass. The Bullet cluster observed in 2006 shows 2 galaxy clusters that collided. The visible matter, hot X-ray emitting gas lags behind, slowed by collision. But gravitational lensing maps show mass concentrations farther ahead, where galaxies pass through each other. The lensing reveals dark matter, which doesn't collide or emit light traveling with the galaxies. Light bends around invisible mass, making it detectable. Brown dwarf atmospheres contain exotic chemistry. Surface temperatures range from 2,500 K for the warmest to 250 K for the coolest, comparable to room temperature. Spectra show water vapor, methane, ammonia, and in some cases molten iron droplets and silicate clouds. The coolest brown dwarfs might have water clouds. These objects blur the boundary between planets and stars. Jupiter radiates more heat than it receives from the sun, leftover energy from formation. Brown dwarfs do the same, but more intensely. Light from failed stars tells chemical stories. The Voyager golden records carry light encoded in grooves. In 1977, both Voyager spacecraft carried gold-plated phonograph records containing sounds and images from Earth. The images' 116 photographs and diagrams were encoded as audio waveforms. An alien civilization would need to decode the signals and reconstruct the images. The cover shows diagrams explaining how to play the record binary numbers and a pulsar map showing Earth's location. Sunlight reflects off the golden surfaces as Voyager 1 crosses interstellar space 24 billion kilometers from Earth. Light carries human messages into the void. Light pollution costs billions in wasted energy. The United States alone wastes about $3 billion annually illuminating the sky. Poorly designed lights shine upward, brightening clouds and atmosphere without illuminating the ground. This represents about 21 million tons of CO2 emissions yearly. Dark sky advocates promote full cutoff fixtures that direct light downward. LED technology allows precise control, but often increases brightness. Negating efficiency gains the rebound effect. Some cities like Flagstaff, Arizona, maintain dark sky ordinances. Light used carelessly becomes both expense and pollution. The green flash appears briefly at sunset or sunrise. As the sun dips below the horizon, atmospheric refraction bends different colors by different amounts. Red light refracted least vanishes first. Blue and violet scatter strongly, leaving green visible for 1 to 2 seconds under ideal conditions. The effect requires a clear, distant horizon ocean or flat plain and stable atmosphere. Jules Verne described it in his 1882 novel Le Rayon Vert, spurring public interest. Spotting a green flash involves luck timing and patience. Light offers rare gifts to the attentive. Bioluminescent bacteria colonize some squid and fish. The Hawaiian bobtail squid hosts Vibrio fischeri bacteria in a light organ. The bacteria glow, and the squid controls the intensity to match moonlight and starlight, filtering down through ocean water. Predators looking up can't see the squid's silhouette counter-illumination camouflage. Each generation of squid must acquire bacteria fresh from seawater. This symbiosis has existed for millions of years. Evolution found partnership through light. Fraunhofer lines are dark absorption lines in the sun's spectrum. In 1814, Joseph von Fraunhofer observed hundreds of these lines, labeling the strongest with letters A through K. The D line corresponds to sodium. The H and K lines come from calcium. These lines form when photons from the hot solar interior pass through cooler outer layers. Atoms in the outer layers absorb specific wavelengths, creating dark lines. By 1860, Gustav Kirchhoff and Robert Bunsen realized these lines revealed the sun's composition. The same elements on Earth exist in the sun. Light disclosed the universe's chemical unity. Streetlights affect plant biology. Artificial light extends perceived day length. Deciduous trees near streetlights delay autumn leaf drop by weeks. Spring bud break occurs earlier. Photoperiod sensitive plants flower at wrong times. Some grow year-round under continuous light-exhausting reserves and dying. Night length triggers many plant physiological processes, dormancy flowering seasonal responses. Disrupting these cycles reduces fitness. Trees stressed by mistimed growth become vulnerable to frost and pests. Light mistimed confuses the biological clocks of flora. The oldest light we can observe is the cosmic microwave background. Emitted 380,000 years after the Big Bang, these photons have traveled 8 billion years. In that time, space expanded by a factor of about 1/100, stretching the photons from visible, infrared, into microwaves. The CMB has a nearly perfect blackbody spectrum at 2.725 Kelvin. Tiny temperature fluctuations, parts per 100,000 map the density variations that seeded galaxies. The Planck spacecraft mapped these fluctuations across the entire sky with unprecedented precision from 2009 to 2013. Light preserves the universe's baby photo in microwave form. Aurora altitude determines color. Red auroras occur above 300 kilometers, where oxygen emits 630 nanometer light. Green auroras dominate between 100 and 300 kilometers oxygen, emitting at 557.7 nanometers. Below 100 kilometers, nitrogen produces blue and purple hues. The colors depend on which atmospheric gases the solar wind particles collide with, and at what altitude. Air density decreases with altitude, affecting collision energies. Sometimes auroras appear pure green. Other times, mixed colors ripple across the sky in curtains and arcs. Light from space creates atmospheric rainbows. Solar storms can disrupt power grids. On March 13, 1989, a coronal mass ejection struck Earth's magnetosphere. Induced currents in Quebec's power grid caused transformers to fail. 6 million people lost power for 9 hours. The 1859 Carrington event was far stronger. Telegraph systems worldwide sparked and caught fire. Auroras appeared near the equator. If such a storm hit today, damage could reach trillions of dollars. Satellites would fail, power grids would collapse, communication systems would go dark. Light's parent star has destructive tantrums. Light carries linear momentum, but also angular momentum. Circularly polarized light has photons with spin angular momentum, either left or right-handed. Light can also carry orbital angular momentum when the wavefront twists helically like a corkscrew. This creates beams with phase singularities darkness at the center. In 1992, Les Allen and colleagues demonstrated light beams carrying orbital angular momentum. These beams can transfer that angular momentum to objects rotating them. Optical spanners manipulate microscopic particles. Light spins as well as pushes. The Hubble constant measures universe expansion rate. Current measurements give about 70 kilometers per second per megaparsec. This means a galaxy 1 megaparsec away, about 3.26 million light-years, recedes at 70 km/L due to space expansion. At 10 megaparsecs, 700 km/s. At great distances, recession velocities exceed light speed. Space itself expands faster than light can travel through it. We can't see those regions. Edwin Hubble discovered this expansion in 1929 using Cepheid variables to measure distances and Doppler shifts to measure velocities. Light revealed the universe grows. Fast radio bursts might repeat. FRB 121102, discovered in 2012, produces bursts irregularly. Astronomers located it to a dwarf galaxy, 3 billion light-years away. The bursts show extreme scattering, suggesting they pass through dense plasma. Leading theories involve magnetars neutron stars with magnetic fields, trillions of times Earth's, somehow producing coherent radio emission. Or perhaps colliding neutron stars, though that couldn't explain repeating bursts. More FRBs are discovered monthly. Most don't repeat. Light's radio siblings arrive as cosmic telegrams without clear authorship. Noctilucent clouds glow at night. These highest clouds, 80 to 85 kilometers altitude, form from ice crystals around meteor dust in the mesosphere. After sunset, when lower atmosphere is dark, sunlight below the horizon still illuminates these high clouds. They appear electric blue rippling across the twilight sky. They're visible only at latitudes above 50 degrees during summer. First recorded in 1885 after Krakatoa's eruption, they may have become more common due to increasing water vapor and methane in the upper atmosphere. Light touches clouds most people never notice. Your lens adjusts focus through accommodation. Ciliary muscles contract, relaxing suspensory ligaments, allowing the lens to bulge. This increases optical power for near vision. The process happens unconsciously controlled by the autonomic nervous system. Young children can accommodate about 15 diopters, focusing objects from infinity down to 7 centimeters. By age 40, accommodation drops to 4 diopters. By 50, about 2 diopters. Reading glasses compensate. The loss is presbyopia, inevitable lens stiffening with age. Light demands flexibility that time erodes. Candlelight flickers at about 1,000 degrees Celsius, hot enough to glow, cool enough to touch near the edges. Humans used candles for 5,000 years before electric lights. Beeswax, tallow, whale oil, paraffin. We burned what we could find. A candle flame produces about 12 lumens, barely enough to read by. People lived by this light for millennia. They went to bed when darkness came. They woke with the sun. Light controlled the rhythm of existence until Edison's bulb changed everything in 1879. Electric light extended the day. Factories ran night shifts. Cities glowed. Productivity increased. But something was lost too. The night became optional. Sleep became negotiable. Your circadian rhythm evolved over millions of years to follow the sun, now receives conflicting signals from screens and streetlights. Blue LEDs suppress melatonin more effectively than any light source in human history. We invented light that actively prevents sleep. Progress and cost intertwined. Light travels through your window every morning. Photons emitted 8 minutes ago at the sun's surface. They dodged Earth's magnetic field, scattered through atmosphere, reflected off walls, and found your eyes. That journey ended in your retina's chemical change, rhodopsin bleaching electrical signals, cascading through bipolar cells and ganglion cells, information racing up the optic nerve to your visual cortex. A single photon absorbed by a single molecule triggering a cascade that generates consciousness of light. You see, because chemistry responds to electromagnetic waves, the moon pulls tides through gravity, but moonlight affects biology through photons. Corals spawn in synchrony during full moons. Certain species of dung beetles navigate using polarized moonlight. Nightjars hunt insects silhouetted against moonlit sky. Your own sleep quality subtly worsens near full moon. Research suggests slight reductions in REM sleep and increased wakefulness. Whether this is an evolutionary remnant or coincidence remains unclear. Light connects organisms across species in ways we're still discovering. Shadows are information. A sundial tells time through shadow position. An X-ray shows bones through differential shadow. Eclipses reveal the moon's orbit and the sun's corona. Cave paintings from 30,000 years ago use shadows and firelight to create flickering animations, bison appearing to run when flames danced. Humans understood shadows before we understood light. Absence teaches presence. Light made photography possible. In 1826, Joseph Nicephore Niepce created the first permanent photograph, a view from his window exposed for 8 hours. Early cameras were chemistry sets. Now they're solid-state electronic silicon photodiodes converting photons to electrons at millions of sites simultaneously. Your phone processes this data through algorithms adjusting exposure, color balance, sharpness. You tap a button. Light becomes memory stored as magnetic domains on a hard drive or charged states in flash memory. Light transforms into magnetism, into electrons, into zeros, and ones into the past, made permanent. Stars are funeral announcements. Betelgeuse shines in Orion's shoulder, about 650 light-years away. If it exploded as a supernova yesterday, you wouldn't know for 650 years. The light reaching your eyes tonight left Betelgeuse around 1374 AD. The star you see might not exist anymore. Every star is a time capsule. The farther you look, the deeper into history you see. Light is the universe's archive delivered on delay. Some photons never interact. A photon can travel billions of years through empty space across galaxies, pass through cosmic voids, and simply miss everything. Never absorbed, never scattered, eternally in transit. Most photons eventually hit something dust gas, a retina, a detector. But some might travel forever through expanding space, cooling, and redshifting until they're undetectable, functionally erased from causality. Light without witnesses. You've been part of this story, since you were born. Photons shaped your vitamin D production. Daylight synchronized your circadian rhythm. Sunlight on your skin triggered melanin production, darkening it for protection. Blue sky taught your visual system color constancy. Reflections in water showed you perspective. Shadows taught depth perception. Every photon that reached your eyes contributed to your neural model of reality. You are in part a construct of accumulated light. Light connects distant strangers. The photon touching your face now might have bounced off a window in Tokyo, reflected from a lake in Finland, scattered through clouds over the Sahara. Light travels fast enough to circle Earth 7 times in 1 second. Someone on the other side of the planet sees their sunrise as you see your sunset. The same star, different angles. Light makes the planet feel small. Firelight brought humans together. Before electric light, people gathered around flames, campfires, hearths, candles. Faces illuminated from below. Stories told in flickering warmth. Fire was safety cooking community. It extended the useful day by hours. Early humans who mastered fire outcompeted those who didn't. Light became survival. We're descendants of the ones who learned to carry light into darkness. You see in color because 3 types of cells evolve sensitivity to different wavelengths: red cones, green cones, blue cones. If you had 4 like some birds, the world would contain colors you can't imagine. If you had 1 like most mammals, everything would be shades of gray. Your experience of a sunset orange fading to purple clouds edged in gold is entirely contingent on your biology. Light is objective. Color is interpretation. What you see is negotiation between physics and perception. The speed of light is finite, but it's fast enough to feel instant. You flip a switch, the room brightens. The delay of few nanoseconds for light to travel from bulb to your eyes is imperceptible. For everyday distances, light might as well be instantaneous. But on cosmic scales, that finite speed creates the light cone, the boundary of what you can ever observe or influence. Events beyond your light cone haven't happened for you yet. Light defines what can be known. Darkness is the natural state. Light is the exception. Most of the universe is empty space, cold, dark, vast. Stars are oases scattered through a desert of nothing. Earth orbits one of perhaps 200 billion stars in the Milky Way. The galaxy contains perhaps 300 billion planets. And there are roughly 2 trillion galaxies in the observable universe. Each galaxy a city of suns. Yet the universe is mostly darkness. Light is rare. You're standing on a tiny island of illumination in an ocean of night. Photosynthesis built the air you breathe. For 2 billion years, cyanobacteria absorbed sunlight and released oxygen as waste. This oxygen accumulated in oceans, then atmosphere rusting iron and changing chemistry planet-wide. Complex life became possible only after oxygen levels rose. Your lungs inhale a gift from ancient microbes that learned to split water using light. Every breath traces back to photons absorbed billions of years ago. Light made the atmosphere. You're made of light in a sense. The energy binding atoms together, the strong nuclear force holding quarks and protons and neutrons, the electromagnetic force holding electrons in orbitals. These forces are mediated by particle exchanges. Photons carry electromagnetic force. Gluons carry strong force. Your body is a standing wave of quantum fields held together by forces that propagate at light speed. You're not separate from light. You're an expression of the same phenomena that makes stars shine. Light has no memory and no future. A photon doesn't experience time. From its perspective, emission and absorption are simultaneous. It doesn't age, doesn't decay, doesn't change. The photon absorbed by your eye is identical to how it was when it left the sun 8 minutes ago, or a star 10 billion years ago. Light exists in an eternal present connecting moments without experiencing duration. Maybe that's the gentlest thought to carry into sleep. Light connects everything stars to eyes past, to present energy to matter distant strangers to each other. It doesn't try, It simply is, and in being it reveals. Not everything, not all at once, just enough to see. You've walked through a universe lit by quantum mechanics and relativity by chemistry and evolution by stars that died before Earth formed. Light brought you here, not just to this moment, but to existence itself. The photons that warmed the early Earth, that powered the first photosynthetic cells, that shaped your ancestors' sleep cycles, that allow you to read these words, it's all the same light, same physics, same constant speed, same tendency to reveal structure hidden in darkness. Rest now. The light will be here tomorrow. It's been here for 13.8 billion years. It'll continue long after you and everything you know has ended. Light is patient, light is constant. Sleep well, dream gently. Good night.